something ancient lurks beneath our feet. Deeper than myth, older than bones. Was Earth once home to a forgotten civilization, one lost so far back, even the rocks barely whisper its name? This is the Silurian hypothesis, a bold idea that humanity may not be the first technological species to walk this world. Imagine cities turned to dust before dinosaurs, their monuments swallowed by time, erased by shifting continents and relentless eons. Scientists digging into Earth's layers have found odd signals, carbon spikes, sudden changes, strange fingerprints that challenge everything we know. If a civilization rose and fell 100 million years ago, would any trace remain? Or would all memory be wiped clean, leaving only riddles in stone? In the end, we're left with a haunting question. How would we ever know if we were not the first? And if we are not, what stories did the Earth forget to tell? The Silurian hypothesis is a thought-provoking concept that challenges our understanding of Earth's history and the potential for advanced civilizations in the distant past. Proposed by scientists Adam Frank and Gavin Schmidt in 2018, this hypothesis asks a compelling question. Could there have been an industrial civilization on Earth millions of years ago, long before humans evolved? Named after a fictional ancient reptilian race from the popular science fiction series Doctor Who, the Silurian hypothesis explores the possibility that a technologically advanced species could have existed on our planet in the deep geological past. The key idea is that if such a civilization had flourished and then disappeared, would we be able to detect evidence of its existence after millions of years? This hypothesis is not suggesting that there actually was an ancient, advanced civilization. Rather, it serves as a thought experiment to consider how we might recognize the signs of industrial activity in the geological record over vast timescales. It also raises questions about the long-term impact of our own civilization on the planet and how future species might interpret the traces we leave behind. The Silurian hypothesis encourages us to think critically about the limitations of our knowledge and the assumptions we make about Earth's past. It reminds us that absence of evidence is not necessarily evidence of absence, especially when dealing with timescales spanning millions of years. The Silurian hypothesis was first proposed by Gavin Schmidt and Adam Frank in 2018. These scientists, both experts in their fields, developed this intriguing concept as a thought experiment to explore the limits of our knowledge about Earth's deep history. Schmidt, a climate scientist, and Frank, an astrophysicist, were pondering the question of how we might detect the existence of an advanced civilization that existed millions of years ago. They named their hypothesis after the fictional Silurians, an ancient reptilian race from the popular science fiction series Doctor Who. The core idea of the Silurian hypothesis is to consider whether it would be possible to find evidence of an industrial civilization that might have existed on Earth many millions of years before our own. This concept challenges our understanding of both Earth's history and our methods of studying the geological record. By proposing this hypothesis, Schmidt and Frank aim to stimulate discussion about the nature of evidence in the geological record and the potential limitations of our knowledge about Earth's past. Their work has sparked interesting debates in the scientific community about how we interpret the traces left behind by civilizations and what this means for our search for extraterrestrial intelligence. The Silurian hypothesis takes its name from a science fiction concept, specifically from the British television series Doctor Who. In the show, the Silurians were an advanced reptilian species that supposedly ruled Earth long before humans evolved. This fictional premise inspired scientists to ponder a serious question. Could there have been an advanced civilization on Earth millions of years ago, long before humans appeared? The term Silurian in geology actually refers to a period of Earth's history from about 443 million to 419 million years ago. During this time, life was flourishing in the oceans, and plants were just beginning to colonize the land. By using this name, the hypothesis playfully suggests we look even further back in time than the actual Silurian period for potential evidence of ancient technological civilizations. Scientists Gavin Schmidt and Adam Frank proposed this thought experiment to consider how we might detect signs of an industrial civilization in the geological record if it had existed millions of years in the past. They weren't suggesting that such a civilization actually existed, but rather using the idea to explore how we might recognize the long-term impact of our own civilization in the far future. This hypothesis challenges us to think about the lasting traces of advanced societies and how they might be preserved or erased over vast spans of geological time. It also prompts us to consider the limits of our knowledge about Earth's distant past and the potential for surprising discoveries in the geological record. The Silurian hypothesis presents a thought-provoking challenge to our conventional understanding of Earth's history. This intriguing concept suggests the possibility that an advanced civilization might have existed on our planet millions of years ago, long before humans emerged. The hypothesis takes its name from a race of reptilian humanoids in the science fiction series Doctor Who, but its implications for real-world science are far-reaching. At its core, the Silurian hypothesis asks us to consider what traces a technologically advanced society would leave behind after millions of years. Given the vast spans of geological time, most evidence of such a civilization would likely be erased by natural processes like erosion, plate tectonics, and weathering. This leads to a fascinating question. How can we be certain that our species is the first to achieve industrial-level technology on Earth? The hypothesis challenges archaeologists and geologists to re-examine the geological record with fresh eyes. It prompts us to consider whether some of the anomalies we find in rock strata or fossil records could potentially be remnants of a long-lost technological society. While there is currently no evidence supporting the existence of such a civilization, the hypothesis serves as a valuable thought experiment. Perhaps most importantly, the Silurian hypothesis encourages us to reflect on our own impact on the planet. By considering how difficult it might be to detect an ancient civilization, we gain perspective on how our current actions might be interpreted by future scientists millions of years from now. This reflection can inform our approach to long-term environmental changes and the geological footprint we are leaving for future generations. The concept of ancient civilizations existing millions of years ago has captivated scientists and researchers for decades. This fascination stems from a combination of archaeological discoveries, geological evidence, and the human desire to understand our place in the universe. One key factor that sparked scientific interest was the discovery of complex structures and artifacts that seemed to defy conventional timelines of human civilization. Underwater ruins, such as those found off the coast of Japan and in the Mediterranean Sea, hinted at the possibility of advanced societies existing before known historical records. These findings challenged scientists to reconsider the age and sophistication of early human cultures. Geological evidence also played a crucial role in inspiring this line of inquiry. The theory of plate tectonics and the understanding of how land masses have shifted over millions of years led scientists to speculate about the potential for lost continents and submerged land masses that could have once hosted advanced civilizations. This geological perspective opened up new avenues for exploring the possibility of extremely ancient human or humanoid societies. Furthermore, the discovery of extinct human species, such as Homo erectus and Neanderthals, expanded our understanding of human evolution and raised questions about the potential technological capabilities of our ancient relatives. This broader view of human history encouraged scientists to consider the possibility of advanced civilizations existing far earlier than previously thought, pushing the boundaries of our understanding of human development and technological progress. The concept of deep time and the Silurian hypothesis intersect in a fascinating exploration of Earth's ancient history and the potential for long-lost civilizations. Deep time refers to the vast expanse of geological time, stretching back billions of years, far beyond human comprehension. This concept is crucial when considering the Silurian hypothesis, which proposes the possibility of advanced civilizations existing on Earth millions of years ago. The Silurian hypothesis, named after a fictional ancient reptilian race from Doctor Who, suggests that if an industrial civilization had existed in the deep past, perhaps tens of millions of years ago, we might have difficulty finding clear evidence of it today. Over such immense timescales, many traces of a civilization could be erased or transformed beyond recognition by geological processes. This hypothesis challenges us to consider how we might detect the remnants of a long-gone technological society in the geological record. It also highlights the limitations of our understanding when dealing with deep time. The Earth has existed for over 4 billion years, and complex life has been around for hundreds of millions of years. Our own civilization represents only a tiny fraction of this vast timeline. The Silurian hypothesis serves as a thought experiment, encouraging scientists to consider how to search for signs of ancient industrial activity in the geological record. It also underscores the importance of studying Earth's deep history to better understand our planet's past and potential future. While there is no evidence supporting the existence of such ancient civilizations, the hypothesis demonstrates the challenges of interpreting the distant past and the need for innovative approaches in paleontology and geology. The Silurian hypothesis proposes that an advanced civilization might have existed on Earth millions of years ago, leaving little to no trace of their presence. This intriguing concept, while speculative, has several arguments supporting its possibility. One key argument is the potential for rapid decay and disappearance of technological artifacts over geological timescales. Given enough time, even our most durable structures and materials would break down, be buried, or be transformed by natural processes. This means that if an ancient civilization existed, its remains might be indistinguishable from natural geological formations. Another supporting argument is the limited nature of our geological record. We have only explored a fraction of Earth's crust, and much of the planet's surface has been recycled through plate tectonics. This leaves open the possibility that evidence of a past civilization could exist in unexplored areas or have been destroyed by natural processes. The hypothesis also considers the potential for non-human intelligence. If an advanced species evolved from a different ancestral line, their physical form and technological choices might differ significantly from ours, making their traces even harder to recognize or interpret correctly. The Silurian hypothesis stands apart from other theories about ancient civilizations by proposing a radical and thought-provoking concept. Unlike traditional theories that focus on human ancestors or lost human civilizations, this hypothesis explores the possibility of an advanced, non-human industrial civilization existing on Earth millions of years before humans evolved. Named after the fictional reptilian race from Doctor Who, the Silurian hypothesis asks a compelling question. If an industrial civilization had existed in Earth's distant past, would we be able to detect it? This idea challenges our understanding of Earth's history and the potential for intelligent life to have evolved before humans. The hypothesis suggests that if such a civilization had existed, most evidence of its presence would have been erased by geological processes over millions of years. This distinguishes it from other ancient civilization theories, which often rely on archaeological evidence. Instead, the Silurian hypothesis proposes looking for subtle geological and chemical signatures that might persist over vast timescales. While highly speculative, this hypothesis serves as a thought experiment to explore how we might detect ancient civilizations on other planets and to consider the long-term impact of our own civilization on Earth's geological record. It encourages us to think beyond human-centric views of Earth's history and consider the possibilities of life and intelligence in forms we might not immediately recognize. The Silurian hypothesis, which explores the possibility of advanced civilizations existing on Earth millions of years ago, draws upon a wide range of scientific disciplines. Geology plays a crucial role, as researchers examine rock layers and sediments for unusual patterns or anomalies that could indicate past technological activity. Paleontology contributes by studying fossil records and searching for any signs of artifacts or structures that might have survived from ancient times. Chemistry and geochemistry are essential for analyzing the chemical composition of rock samples and identifying any unusual concentrations of elements or compounds that might suggest industrial processes. Climate science helps in reconstructing past environmental conditions and investigating potential anthropogenic climate changes that could have occurred in deep time. Astronomy and astrophysics provide context by studying the conditions necessary for life to evolve and thrive on planets, while also considering the potential impact of cosmic events on Earth's history. Archaeology, though typically focused on more recent human history, offers valuable methodologies for interpreting potential evidence of past civilizations. Interdisciplinary fields such as astrobiology and exoplanetology contribute to the investigation by considering the broader implications of advanced life existing on Earth or other planets in the distant past. This diverse array of scientific disciplines collaborates to examine the intriguing possibility of ancient, technologically advanced societies on our planet, challenging our understanding of Earth's history and the potential for intelligent life in the universe. The Silurian hypothesis, proposed by scientists Gavin Schmidt and Adam Frank, has sparked intriguing discussions within the scientific community. This thought experiment explores the possibility of an advanced industrial civilization existing on Earth millions of years before humans. While the hypothesis is not widely accepted as a serious scientific theory, it has been acknowledged as a valuable tool for considering the long-term impact of human civilization on our planet. Many scientists appreciate the hypothesis for its ability to highlight the challenges in detecting ancient technological societies in the geological record. It emphasizes how quickly evidence of our own civilization might disappear over geological timescales, raising important questions about our understanding of Earth's history and our place in it. However, most experts in paleontology and geology remain skeptical of the actual existence of such an ancient civilization. They point out the lack of concrete evidence in the fossil record or geological strata that would support the presence of an advanced industrial society millions of years ago. The absence of artifacts, chemical signatures, or other telltale signs of technology makes the hypothesis highly improbable in their view. Despite this skepticism, the Silurian hypothesis has proven valuable in encouraging scientists to consider new ways of looking for signs of past civilizations and to reflect on the long-term consequences of our own industrial activities. It has also contributed to discussions about the search for extraterrestrial intelligence by highlighting the difficulties in recognizing technological civilizations over vast timescales. Earth formed approximately 4.5 billion years ago, a figure determined through extensive geological research and radiometric dating techniques. Scientists have analyzed ancient rocks and minerals, including zircon crystals from Australia, that are nearly 4.4 billion years old. These crystals provide crucial evidence for Earth's early formation. Meteorites have also played a significant role in determining our planet's age. These space rocks, remnants from the early solar system, have been dated to around 4.6 billion years. Their age closely matches that of Earth, supporting the theory that our planet formed during the early stages of the solar system's development. The age of Earth is further corroborated by studying the decay of radioactive isotopes in rocks from Earth and the Moon. This method, known as radiometric dating, allows scientists to calculate the time since these rocks solidified. By combining multiple lines of evidence, researchers have confidently established Earth's age at approximately 4.5 billion years. Understanding Earth's age provides crucial context for studying the evolution of life, geological processes, and the broader history of our solar system. It serves as a foundation for numerous scientific disciplines, from paleontology to planetary science, shaping our understanding of Earth's place in the cosmos. Scientists divide Earth's history into different eras by examining the geological record and the evolution of life on our planet. This timeline, known as the geologic timescale, is based on evidence found in rock layers, fossils, and other geological features. The largest divisions of Earth's history are called eons, which are further divided into eras, periods, and epochs. The current eon, the Phanerozoic, began about 541 million years ago and is characterized by the abundance of complex life forms. It is divided into 3 eras: the Paleozoic, Mesozoic, and Cenozoic. Each era is marked by significant changes in Earth's flora and fauna, often coinciding with major geological events or mass extinctions. For example, the Mesozoic era, known as the Age of Reptiles, saw the rise and fall of the dinosaurs. It ended with a mass extinction event about 66 million years ago, likely caused by an asteroid impact. Scientists use various dating methods to determine the age of rocks and fossils, including radiometric dating and the study of index fossils. These techniques allow researchers to create a detailed timeline of Earth's history, helping us understand the long and complex story of our planet's development. 100 million years ago, Earth was a dramatically different world from the one we know today. The continents were in different positions, with the supercontinent Gondwana slowly breaking apart. The climate was much warmer, with no polar ice caps and sea levels significantly higher than they are now. Lush rainforests covered much of the land, extending even to the poles. This was the middle of the Cretaceous period, and dinosaurs ruled the Earth. Massive sauropods roamed the forests, while fearsome predators like Tyrannosaurus rex had yet to evolve. The skies were filled with pterosaurs, ancient flying reptiles, some with wingspans as wide as small airplanes. In the oceans, massive marine reptiles like plesiosaurs and mosasaurs dominated, while the first flowering plants were beginning to appear on land. The atmosphere during this time contained much more carbon dioxide than it does today, contributing to the greenhouse effect that kept the planet warm. Oxygen levels were also higher, allowing insects and other arthropods to grow to enormous sizes. Giant dragonflies with wingspans of over 2 feet zipped through the air, while meter-long millipedes crawled on the forest floor. This ancient Earth was a world of extreme biodiversity, with life flourishing in forms that would seem alien to us today. The continents continued to drift, climates shifted, and species evolved, setting the stage for the emergence of mammals and eventually humans millions of years later. This snapshot of Earth's past reminds us of the constant change our planet undergoes and the incredible diversity of life it has supported throughout its long history. 100 million years ago, our planet was in the midst of the Cretaceous period, a time of remarkable change and diversity in Earth's history. This extensive geological era began approximately 145 million years ago and lasted until about 66 million years ago, spanning nearly 80 million years. The Cretaceous was characterized by a warm greenhouse climate, with sea levels much higher than they are today. Vast inland seas covered large portions of the continents, creating new habitats and influencing global weather patterns. This period saw the continued breakup of the supercontinent Pangaea, with land masses slowly drifting towards their present-day positions. During this time, life on Earth was thriving and evolving rapidly. The Cretaceous witnessed the dominance of dinosaurs, with iconic species like Tyrannosaurus rex and Triceratops roaming the land. In the oceans, giant marine reptiles such as mosasaurs and plesiosaurs ruled the waters, while the skies were filled with pterosaurs and the first true birds. Perhaps most significantly, the Cretaceous period saw the rise and diversification of flowering plants, transforming terrestrial ecosystems and setting the stage for the world we know today. This period ended with one of the most famous mass extinction events in Earth's history, marking the end of the age of dinosaurs and paving the way for the rise of mammals. 100 million years ago, during the Mid-Cretaceous period, Earth was a world dominated by reptiles, with dinosaurs reigning supreme on land. Massive sauropods like Argentinosaurus, among the largest land animals ever to exist, roamed vast forests and plains. Fearsome predators such as Tyrannosaurus rex had not yet evolved, but their predecessors, including Allosaurus and early tyrannosaurs, were apex predators of their time. In the skies, pterosaurs were the masters of flight. These flying reptiles, not dinosaurs themselves, included species with wingspans over 10 meters wide. The oceans teemed with marine reptiles, including long-necked plesiosaurs, dolphin-like ichthyosaurs, and massive mosasaurs, which were essentially sea-going lizards that grew to lengths of 15 meters or more. While reptiles dominated, mammals were present, but remained small and mostly nocturnal. These early mammals, our distant ancestors, lived in the shadows of the dinosaurs, waiting for their moment to diversify and thrive. Plants were also undergoing significant changes, with flowering plants beginning to spread and diversify, gradually transforming the landscape. This period was a time of warm global temperatures and high sea levels, creating lush tropical environments even at high latitudes. The world was very different from what we know today, with continents still in the process of breaking apart and the Atlantic Ocean continuing to widen. Earth's continents have undergone dramatic transformations over the past 100 million years, driven by the relentless forces of plate tectonics. 100 million years ago, during the Cretaceous period, the continents were arranged quite differently from today. The supercontinent Pangaea had already broken apart, but the resulting land masses were still clustered much closer together. South America and Africa had begun to separate, creating a narrow Atlantic Ocean between them. India was an island continent, drifting northward across the ancient Tethys Sea. North America was connected to Europe, while Australia remained joined to Antarctica. As time progressed, these continents continued their slow but steady journey across the globe. The most significant changes occurred as India collided with Asia, a process that began around 50 million years ago and continues today. This monumental collision resulted in the formation of the Himalayas, the world's highest mountain range. Meanwhile, South America completely separated from Antarctica and moved northward, eventually colliding with North America to form the Isthmus of Panama. Australia also played a crucial role in shaping our modern world. It separated from Antarctica and moved northward, altering global ocean currents and contributing to the cooling of the Earth's climate. Africa continued its northward journey, closing the Tethys Sea and creating the Mediterranean. These continental movements have profoundly influenced Earth's climate, ecosystems, and the evolution of life, shaping the world we know today. 100 million years ago, during the Mid-Cretaceous period, Earth was undergoing significant geological changes. The supercontinent Pangaea had already broken apart, and the continents were drifting towards their current positions. This period saw intense tectonic activity, with the continued separation of South America from Africa and the widening of the Atlantic Ocean. The global climate was much warmer than today, with no polar ice caps. Sea levels were significantly higher, submerging large portions of the continents and creating vast, shallow seas. These conditions led to the formation of extensive chalk deposits, which give the Cretaceous period its name. Volcanic activity was particularly pronounced during this time. The formation of large igneous provinces, such as the Kerguelen Plateau in the southern Indian Ocean, released massive amounts of carbon dioxide into the atmosphere, contributing to the greenhouse effect and global warming. This period also saw the early stages of the formation of the Deccan Traps in India, though the main phase of this enormous volcanic event would occur later, near the end of the Cretaceous. The Mid-Cretaceous was also a time of mountain building. The Andes were beginning to form as the Nazca Plate subducted beneath the South American plate. In North America, the severe orogeny was in full swing, creating a chain of mountains along the western edge of the continent. These geological events shaped the Earth's surface and influenced the evolution of life, setting the stage for the world we know today. Scientists employ several sophisticated methods to determine the age of rocks and fossils, each offering a window into Earth's ancient past. One of the most common techniques is radiometric dating, which measures the decay of radioactive isotopes within the material. This process relies on the predictable rate at which certain elements break down over time, allowing researchers to calculate how long ago the rock or fossil formed. For younger samples, carbon-14 dating is particularly useful. This method examines the ratio of carbon-14 to carbon-12 in organic materials, providing accurate age estimates for items up to about 50,000 years old. However, for older specimens, scientists turn to other radioactive elements with longer half-lives, such as potassium-40 or uranium-238. Geologists also use relative dating techniques to establish the sequence of geological events. By studying the layers of rock in which fossils are found, they can determine which fossils are older, or younger relative to each other. This method, known as stratigraphy, helps create a timeline of Earth's history, even when exact dates are not available. In some cases, scientists combine multiple dating methods to cross-verify their findings and increase accuracy. These techniques, along with advanced technology and careful analysis, allow researchers to piece together the puzzle of our planet's geological and evolutionary history, revealing the age of rocks and fossils with remarkable precision. The Cretaceous period stands as a pivotal chapter in Earth's history, spanning from 145 million years ago to 66 million years ago. This era saw the continued dominance of dinosaurs, but also ushered in significant changes that would shape the modern world. During the Cretaceous, the supercontinent Pangaea continued to break apart, leading to the formation of new oceans and the repositioning of landmasses. This tectonic activity influenced global climate patterns and created diverse environments, fostering the evolution of new species. The period witnessed an explosion of flowering plant diversity, revolutionizing terrestrial ecosystems and providing new food sources for animals. In the oceans, modern groups of plankton emerged, altering marine food webs and leaving behind vast chalk deposits that give the Cretaceous its name. The seas were ruled by fearsome marine reptiles like mosasaurs and plesiosaurs, while in the skies, pterosaurs reached enormous sizes. The Cretaceous period ended with one of the most famous events in Earth's history: a massive asteroid impact that triggered a global catastrophe. This event caused the extinction of non-avian dinosaurs and many other species, marking the end of the Mesozoic era and paving the way for the rise of mammals in the following Cenozoic era. The Cretaceous thus represents both the pinnacle of the age of dinosaurs and the dramatic transition to our modern world. Understanding Earth's geological timeline is crucial when evaluating the Silurian hypothesis, which proposes the possibility of an advanced civilization existing on Earth millions of years ago. Our planet's geological record provides a detailed history stretching back billions of years, allowing scientists to examine evidence of past events and conditions. The Silurian hypothesis challenges us to consider whether signs of an ancient technological civilization could be detected in the geological record. By studying rock layers, fossil distributions, and chemical compositions throughout Earth's history, researchers can look for anomalies or patterns that might indicate the presence of an advanced society predating humans. However, the vast timescales involved present significant challenges. Over millions of years, geological processes such as plate tectonics, erosion, and sedimentation can erase or obscure potential evidence. Understanding these processes and their effects over time is essential for evaluating any claims of ancient civilizations. Moreover, our knowledge of Earth's geological timeline helps contextualize the conditions necessary for complex life and technological development. By examining past climate patterns, atmospheric compositions, and major extinction events, scientists can assess the likelihood of an advanced civilization arising and thriving during specific periods of Earth's history. Scientists exploring the Silurian hypothesis would search for a variety of telltale signs from Earth's distant past. They would examine geological strata for unusual patterns or anomalies that could indicate the presence of an advanced civilization millions of years ago. This might include traces of synthetic materials such as plastics or alloys that would be out of place in ancient rock formations. Researchers would also analyze ice cores and sediment samples for chemical signatures that might suggest large-scale industrial activity. This could include elevated levels of certain pollutants or isotopes associated with nuclear technology. They would look for evidence of large-scale mining operations or other resource extraction activities that might have left lasting marks on the landscape. Paleontologists would be on the lookout for fossilized remains that seem out of place or exhibit signs of modification by intelligent beings. This could include bones with unnatural cut marks or artifacts that appear to be tools or manufactured objects. Astronomers might search for signs of ancient satellite technology or space exploration efforts in the geological record. Ultimately, Supporting the Silurian hypothesis would require finding multiple lines of evidence that converge to suggest the existence of an advanced civilization predating known human history. This would necessitate a careful, multidisciplinary approach to piece together a picture of Earth's potential technological past. Human-made structures leave varying imprints on the geological record, with their longevity depending on factors such as construction materials, environmental conditions, and geological processes. Most modern buildings and infrastructure have a relatively short lifespan in geological terms, often lasting only a few decades to centuries before deteriorating or being replaced. However, some ancient structures have demonstrated remarkable durability. The Egyptian pyramids, built around 4,500 years ago, stand as testament to human engineering and have left a significant mark on the landscape. Similarly, remnants of Roman roads and aqueducts persist after 2,000 years, though often in fragmentary form. In contrast, many contemporary structures are unlikely to leave lasting traces. Steel and concrete, common in modern construction, can corrode and crumble within a few hundred years without maintenance. Even so, human activity is creating new geological markers. Plastic waste, for instance, is forming distinctive layers in sedimentary deposits that may persist for thousands of years. Ultimately, while individual structures may not endure, the collective impact of human civilization is creating a new geological epoch known as the Anthropocene. This human-induced change to the Earth's systems may leave a detectable signature in the rock record for millions of years to come, long after our buildings have turned to dust. Throughout history, various anomalous artifacts and structures have captured the imagination of researchers and the public alike, sparking debates about their origins and potential significance. One such example is the Antikythera mechanism, an ancient Greek device discovered in a shipwreck. This complex mechanical calculator, dating back to around 150 to 100 BCE, has astounded scientists with its sophisticated gears and ability to predict astronomical positions and eclipses. Another intriguing artifact is the Baghdad Battery, a set of terracotta pots containing copper cylinders and iron rods discovered in Iraq. Some researchers have suggested these objects, dating back to the Parthian period, might have been used as primitive electrical devices, though this interpretation remains controversial among archaeologists and historians. In terms of structures, the megalithic site of Göbekli Tepe in Turkey has challenged our understanding of prehistoric societies. Predating Stonehenge by thousands of years, this complex of massive stone pillars adorned with animal carvings has led some to question the conventional timeline of human civilization and technological development. The Nazca lines in Peru, enormous geoglyphs etched into the desert floor, have also been the subject of much speculation. These intricate designs, only fully visible from the air, have led some to propose they were created with the aid of advanced technology or aerial guidance, though most archaeologists attribute their creation to the ancient Nazca culture using simple tools and techniques. Scientists employ a range of techniques to differentiate between natural formations and potential artificial structures. They begin by examining the shape, symmetry, and regularity of the object or structure in question. Natural formations often exhibit irregular patterns and asymmetry, while artificial structures tend to have more uniform and geometric shapes. Detailed analysis of the materials and composition is crucial. Scientists use spectrometry and other advanced imaging techniques to determine the chemical makeup of the object. If the materials are inconsistent with the surrounding environment or show signs of processing, this might indicate artificial origin. Context and location play a significant role in the assessment. Scientists consider the geological and environmental factors that could have shaped the formation naturally. They look for similar structures in the area and evaluate whether known natural processes could explain their existence. In some cases, scientists conduct comparative studies with confirmed artificial structures and natural formations to identify distinguishing characteristics. They also use advanced dating methods to determine the age of the object and compare it with the geological timeline of the area. These multifaceted approaches help scientists make informed judgments about the origin of mysterious structures or objects. Advanced imaging technology has revolutionized the search for ancient civilizations, allowing archaeologists to peer beneath the earth and uncover hidden secrets without disturbing a single grain of soil. Satellite imagery and remote sensing techniques have become indispensable tools, enabling researchers to identify potential sites from high above the ground. These methods can detect subtle changes in vegetation and soil composition that might indicate buried structures or long-lost settlements. LIDAR, which stands for Light Detection and Ranging, has proven particularly valuable in this quest. By firing rapid pulses of laser light at the ground and measuring the reflected signals, LIDAR can create detailed three-dimensional maps of terrain, even penetrating dense forest canopies. This technology has led to remarkable discoveries, such as revealing the true extent of ancient Mayan cities hidden beneath the jungles of Central America. Ground-penetrating radar is another crucial tool in the archaeological arsenal. It allows researchers to create images of what lies beneath the surface without the need for excavation. This non-invasive approach is especially useful in delicate or sacred sites where traditional digging might be impractical or forbidden. By sending radio waves into the ground and analyzing their reflections, archaeologists can identify buried walls, tombs, and other structures. These advanced imaging technologies not only help in discovering new sites, but also in understanding known ones better. They allow for comprehensive mapping of large areas, revealing the layout of entire cities and the relationships between different structures. This broader perspective helps archaeologists piece together a more complete picture of ancient civilizations, their urban planning, and how they interacted with their environment. Throughout Earth's vast landscapes, several intriguing geological features have sparked debate among scientists and historians alike, with some suggesting possible links to ancient civilizations. One such enigma is the Bimini Road in the Bahamas, a submerged rock formation that appears eerily linear and methodical. While many geologists argue it is a natural occurrence, others speculate it could be remnants of an ancient harbor or road. In South America, the Nazca lines continue to perplex researchers. These enormous geoglyphs etched into the desert floor of Peru are visible only from great heights, leading to questions about how and why an ancient culture created them without the ability to see them from above. Although their purpose remains a mystery, they undoubtedly represent a remarkable feat of early engineering and artistic expression. The underwater structures off the coast of Yonaguni, Japan, present another geological puzzle. These massive stone formations exhibit unusually angular features and terraced appearances that some interpret as evidence of human modification. However, the scientific consensus leans towards a natural explanation, attributing the structures to underwater tectonic activity and erosion patterns. In Bosnia, a cluster of hills known as the Bosnian Pyramids has garnered attention due to their unusually symmetrical shapes. While mainstream archaeologists dismiss claims of artificial construction, proponents argue these hills might conceal ancient pyramids beneath layers of soil and vegetation. As with many such sites, the debate continues, highlighting the ongoing fascination with potentially undiscovered ancient wonders hidden within our planet's geology. Researchers employ a variety of sophisticated techniques to investigate submerged landscapes for signs of ancient habitation. Underwater archaeology has become an increasingly important field as sea levels have risen over millennia, covering once-inhabited coastal areas. One key method is the use of side-scan sonar, which creates detailed images of the seafloor. This technology can reveal structures and artifacts that might indicate human presence, such as stone walls, hearths, or even ancient roads. Multi-beam echo sounders complement this approach by producing three-dimensional maps of underwater terrain, helping archaeologists identify promising sites for further investigation. Once potential areas of interest are located, researchers often employ remotely operated vehicles equipped with high-definition cameras and robotic arms. These devices allow for close-up examination and even collection of samples without the need for divers, especially in deeper waters. In shallower areas, teams of trained archaeological divers conduct careful surveys, documenting and excavating sites, much like their land-based counterparts. Advancements in underwater excavation techniques have also played a crucial role. Researchers now use specialized tools, such as water dredges and airlift devices, to carefully remove sediment without damaging delicate artifacts. Additionally, cutting-edge dating methods, including underwater-adapted radiocarbon dating and optically stimulated luminescence, help scientists determine the age of submerged sites and artifacts, providing valuable insights into ancient coastal settlements and migration patterns. Ice core samples are invaluable time capsules that offer a wealth of information about Earth's past climate and environment. These cylindrical samples, extracted from the polar ice sheets of Antarctica and Greenland, contain layers of ice that have accumulated over hundreds of thousands of years. Each layer in an ice core represents a specific period in Earth's history, with the deepest layers being the oldest. As snow falls and compresses into ice, it traps tiny bubbles of air, dust particles, and other materials from the atmosphere. By analyzing these trapped components, scientists can reconstruct past climate conditions, including temperature, precipitation patterns, and atmospheric composition. While ice cores primarily provide data about Earth's climate history, they can also offer indirect evidence about human activities and potential civilizations. For instance, ice cores have revealed increased levels of lead in the atmosphere during the time of the Roman Empire, likely due to extensive metal smelting operations. Similarly, cores have shown spikes in methane levels that coincide with the expansion of rice cultivation in Asia thousands of years ago. However, it is important to note that ice cores cannot directly provide evidence of specific civilizations or human settlements. Their primary value lies in revealing global environmental changes that may have influenced human activities and migrations throughout history. By combining ice core data with other archaeological and geological evidence, scientists can paint a more comprehensive picture of Earth's past and the complex interactions between climate, environment, and human societies. Scientists employ a variety of sophisticated techniques to search for chemical signatures that could hint at past technological activity. One key approach involves analyzing the atmospheric composition of distant planets and moons. Using powerful telescopes and spectroscopy, researchers can detect the presence of specific molecules that might be byproducts of industrial processes or other technological activities. Another method focuses on examining geological samples for unusual concentrations of elements or isotopes that are not typically found in nature. For instance, the presence of certain radioactive isotopes or rare earth elements in high concentrations could suggest artificial enrichment or manipulation. Scientists also look for synthetic compounds that do not occur naturally, as these could be clear indicators of technological intervention. In our own solar system, space probes and landers play a crucial role in this search. These robotic explorers can directly sample the soil, rocks, and atmosphere of other planets and moons, providing detailed chemical analyses that might reveal traces of past technological activity. For example, the Mars rovers have been equipped with instruments capable of detecting organic molecules that could be linked to past life or even remnants of technology. Researchers also consider the potential long-term effects of technology on a planetary scale. This includes searching for signs of large-scale environmental changes that might have been caused by advanced civilizations, such as evidence of planetary engineering or resource exploitation. By combining these various approaches, scientists hope to uncover any subtle clues that might point to the existence of past technological civilizations in our cosmic neighborhood. Uncovering evidence of ancient civilizations from millions of years ago presents numerous challenges for scientists and researchers. The passage of time itself is a significant obstacle, as millions of years of geological processes can dramatically alter or completely erase traces of past societies. Erosion, tectonic activity, and climate changes over such vast timescales can destroy or bury potential artifacts and structures deep beneath the Earth's surface. Organic materials, which often provide valuable insights into ancient cultures, would have long since decomposed, leaving little to no trace for modern researchers to analyze. Another major hurdle is the technological limitations of early civilizations. If advanced societies existed millions of years ago, their technology might have been primarily biological or chemical in nature, leaving few lasting remnants compared to the metal and stone artifacts we associate with more recent civilizations. Additionally, our current methods of dating and analysis may not be suitable for accurately identifying or studying evidence from such distant time periods. Furthermore, our understanding of what constitutes evidence of civilization might be too narrow. An advanced society from millions of years ago could have developed in ways utterly foreign to our current conceptions, making their traces difficult to recognize or interpret correctly. These challenges require scientists to remain open-minded and continually develop new techniques and technologies to probe deeper into Earth's distant past. An advanced civilization from 100 million years ago could have developed truly extraordinary technologies beyond our current comprehension. They might have mastered the manipulation of gravity, allowing them to construct massive structures both on planets and in space. These beings could have created propulsion systems capable of near light-speed travel, enabling exploration of vast regions of the galaxy. Energy production would likely be incredibly efficient, possibly harnessing the power of stars or even the fundamental forces of the universe itself. They might have developed ways to create and stabilize wormholes, allowing instantaneous travel across enormous distances. Advanced artificial intelligence could be seamlessly integrated into all aspects of their society, managing complex systems and solving problems on a cosmic scale. Nanotechnology could have reached a level where they could manipulate matter at the atomic scale with ease, leading to materials with properties we can scarcely imagine. They might have technologies to control weather and climate on a planetary scale, terraform inhospitable worlds, or even create artificial planets or habitats. Perhaps most intriguingly, they could have developed ways to interface directly with the fabric of space-time, or even to perceive and interact with multiple dimensions beyond our current understanding of the universe. Such a civilization might have technologies that, to us, would be indistinguishable from magic, reshaping reality itself to suit their needs and expanding the very boundaries of what we consider possible. Millions of years from now, the geological record would tell a fascinating story of our modern technological era. As layers of sediment build up over time, they would entomb and preserve traces of our civilization in what geologists call the technosphere. In urban areas, the most obvious remnants would be our buildings and infrastructure. Concrete structures, while eventually crumbling, would leave distinct patterns and chemical signatures in the rock. Metal objects like cars, bridges, and skyscrapers would largely corrode, but their outlines and some components might persist as fossil imprints or mineral deposits. Perhaps most telling would be the presence of plastics and electronic waste. These materials, so ubiquitous in our daily lives, do not exist naturally and would form unique layers in the rock record. Plastics, being incredibly durable, might even create entirely new types of rock as they slowly break down and combine with other sediments. Radiation anomalies from nuclear power plants and weapons testing would also leave a lasting imprint. These would be detectable as unusual concentrations of radioactive isotopes in certain rock layers, providing clear evidence of advanced technology. Future geologists, should they exist, would find our era marked by an unprecedented array of artificial materials and chemical signatures, unlike any other period in Earth's history. In the realm of long-lasting materials, certain substances stand out for their remarkable durability. Ceramics, particularly those made from zirconium dioxide, also known as zirconia, show exceptional resistance to degradation over vast timescales. These advanced ceramics are used in various technological applications, from cutting tools to medical implants, and their chemical stability suggests they could endure for millions of years. Certain metals and alloys also demonstrate impressive longevity. Gold, renowned for its resistance to corrosion, could potentially survive for eons in recognizable form. Stainless steel, an alloy containing chromium, forms a protective oxide layer that significantly slows its degradation, making it another candidate for long-term survival. Synthetic materials like certain plastics, while often considered environmentally problematic in the short term, may ironically be among the longest-lasting remnants of our technology. Some plastics, such as polyethylene used in numerous products, degrade extremely slowly under normal environmental conditions and could persist for millions of years. Interestingly, some of the most durable materials are also found in everyday items. The silicon dioxide in glass is incredibly stable and resistant to weathering. Given the right conditions, glass objects could potentially survive for millions of years, offering future civilizations or species a glimpse into our technological era. Ancient civilizations' energy production methods could leave distinct signatures in the geological record, offering clues to their technological advancements. One potential indicator would be unusual concentrations of certain elements or isotopes in sediment layers corresponding to the time period of the civilization. For instance, extensive use of fossil fuels might result in elevated levels of carbon and sulfur in soil samples. Mining activities could leave behind telltale signs such as altered landscapes, concentrated deposits of metal ores, or unusual mineral distributions. These changes might be detectable through geological surveys or core samples taken from relevant sites. Additionally, large-scale deforestation for fuel would be reflected in pollen records, showing a sudden shift in vegetation patterns. Advanced civilizations might have harnessed nuclear energy, which could leave long-lasting radioactive isotopes in the environment. Anomalous levels of elements like plutonium or unusual ratios of uranium isotopes might indicate past nuclear activity. Similarly, extensive use of geothermal energy could alter the thermal properties of surrounding rock formations, potentially detectable through careful analysis. Ultimately, the key to identifying ancient energy production lies in recognizing patterns and anomalies that deviate from natural geological processes. By combining multiple lines of evidence from geology, chemistry, and archaeology, scientists can piece together a picture of how past civilizations might have powered their societies, offering valuable insights into their technological capabilities and environmental impact. Ancient mining and resource extraction activities could leave behind a variety of telltale signs, even after thousands or millions of years. On Earth, we can look to our own history for clues about what such traces might entail on other worlds. Large-scale excavations would be one of the most obvious indicators. Open pit mines, quarries, and strip mining operations can dramatically alter landscapes, creating artificial depressions, cliffs, and plateaus that might persist long after the civilization that created them has vanished. These features could potentially be visible from orbit, especially if they occurred on a massive scale. Underground operations might leave behind networks of tunnels and shafts. While many of these could collapse over time, some might remain intact, particularly in geologically stable areas or if reinforced with durable materials. Explorers might stumble upon these subterranean passages, finding them lined with tool marks or containing abandoned equipment. Waste products from mining and refining processes could also endure. Tailings, piles, slag heaps, and other accumulations of discarded materials might form distinctive mounds or change the chemical composition of surrounding soils. This could lead to unusual patterns of mineral deposits or vegetation growth that stand out from natural formations. Identifying advanced agricultural practices from millions of years ago presents significant challenges, but scientists employ various techniques to uncover evidence of ancient farming methods. Archaeologists and paleobotanists examine fossilized plant remains, pollen records, and soil samples to detect signs of early crop cultivation and land management. These experts look for changes in plant species composition, alterations in pollen distribution patterns, and modifications to soil structure that might indicate deliberate agricultural activities. Sophisticated imaging technologies, such as ground-penetrating radar and satellite imagery, allow researchers to detect subtle changes in landscape features that could be remnants of ancient field systems or irrigation networks. These methods can reveal patterns of land use that are not visible to the naked eye. Providing valuable insights into prehistoric farming practices, Chemical analysis of ancient human remains and artifacts can also offer clues about past agricultural activities. By examining isotope ratios in bones and teeth, scientists can infer information about diet and food production methods. Additionally, residue analysis on pottery and tools might reveal traces of cultivated plants or agricultural products, shedding light on the types of crops grown and processing techniques used. Genetic studies of modern crop species and their wild relatives can help trace the history of plant domestication and breeding. By analyzing the DNA of contemporary plants, researchers can reconstruct the evolutionary pathways of important crops, potentially identifying when and where specific agricultural innovations occurred. This genetic evidence, combined with archaeological findings, helps paint a clearer picture of ancient agricultural practices and their development over time. Archaeologists use various clues to identify ancient urban centers. One key indicator is the presence of large-scale architectural remains, such as foundations of buildings, walls, and fortifications. These structures often form distinct patterns that suggest organized city planning. Another important piece of evidence is the concentration of artifacts in a specific area. This might include pottery shards, tools, and other everyday objects that indicate dense human habitation. The diversity and quantity of these artifacts can provide insights into the size and complexity of the ancient settlement. Modifications to the landscape also offer valuable evidence. Ancient cities often left lasting imprints on their surroundings, such as irrigation systems, terraced hillsides, or altered watercourses. These changes reflect the ways in which early urban dwellers adapted their environment to support larger populations. Written records, when available, provide crucial information about ancient urban centers. Inscriptions, clay tablets, or other forms of documentation can offer direct evidence of city names, rulers, and daily life. Even in the absence of written language, symbolic representations like rock art or carved symbols can indicate the presence of complex societies capable of supporting urban environments. Ancient transportation systems can leave subtle but detectable traces in the geological record. One key indicator is the presence of linear features in landscapes that persist over long periods. These might appear as faint lines or paths visible in satellite imagery or aerial photographs, often following routes that make sense for ancient travel between settlements or resources. Geologists and archaeologists also look for changes in soil composition along potential routes. The repeated passage of people, animals, and vehicles can compact soil and alter its chemical makeup. This can be detected through careful analysis of soil samples, revealing higher concentrations of certain elements associated with human activity. In some cases, ancient roads or paths might be preserved beneath layers of sediment. When excavated, these can reveal engineered surfaces, such as packed gravel or stone paving. Additionally, erosion patterns can provide clues, as well-traveled routes might show distinctive wear patterns in rock formations or river crossings. Artifacts found along suspected routes can also indicate ancient transportation systems. These might include items lost during travel, such as coins, pottery shards, or tools. The distribution of such artifacts can help map out ancient networks of movement and trade, providing insights into how our ancestors navigated their world. Traces of advanced medical and biological technology that could survive for millions of years would likely be limited to the most durable and stable materials. Synthetic polymers, such as certain plastics, could potentially endure for extremely long periods, especially if buried in sediments or protected from degrading factors. These might preserve shapes or structures of medical devices or tools. Metallic implants or prosthetics made from titanium or other corrosion-resistant alloys could also persist for vast stretches of time. These materials resist breakdown and could retain their form long after the organisms they were part of have decomposed. In some cases, these artifacts might even become fossilized, encased in mineral deposits that further protect them from decay. At the molecular level, engineered DNA or synthetic genetic materials might leave detectable traces in the fossil record. While natural DNA degrades relatively quickly, specially designed genetic structures or artificial nucleic acids could potentially have greater longevity. These might be discoverable through advanced analytical techniques applied to fossilized remains. Lastly, large-scale biological engineering projects, such as genetically modified organisms or entire ecosystems, might leave lasting impacts on the evolutionary trajectory of species. These changes could be detectable through comparative genomics or paleoecological studies, revealing the influence of advanced biological manipulation long after the technology itself has disappeared. Ancient space exploration efforts, if they existed, would leave behind distinct traces that modern scientists could potentially identify. On Earth, we might find anomalous artifacts or structures that defy conventional historical explanations, possibly buried deep within geological strata or hidden in remote locations. These could include advanced materials or technologies inconsistent with known ancient capabilities. In our solar system, evidence might take the form of artificial objects or alterations on other celestial bodies. Unusual formations on the Moon or Mars, for example, could indicate past visitations or even attempts at colonization. Long-lived spacecraft or satellites in unusual orbits might also suggest ancient space activities. Beyond our solar system, scientists could search for signs of megastructures or other large-scale engineering projects around distant stars. These might include Dyson spheres, designed to capture a star's energy, or intentional alterations to stellar output as a form of long-distance communication. Astronomical observations might also reveal evidence of interstellar travel, such as unexplained propulsion signatures or the presence of artificial materials in space. However, distinguishing such evidence from natural phenomena would require extremely precise measurements and careful analysis to avoid false positives. Uncovering evidence of ancient civilizations from 100 million years ago presents numerous challenges for scientists and researchers. The immense span of time separating us from that era has erased most traces of potential intelligent life, making the search incredibly difficult. One major obstacle is the constant recycling of Earth's crust through plate tectonics. Over millions of years, entire continents have shifted, merged, and been subducted beneath one another. This process effectively destroys or buries any surface-level artifacts or structures that might have existed. Even if an advanced civilization had built impressive monuments or cities, they would likely have been crushed, melted, or pushed deep into the Earth's mantle by now. The forces of erosion and weathering also pose significant challenges. Wind, water, and ice have reshaped the planet's surface countless times over the past 100 million years, wearing away any potential evidence. Landscapes have been dramatically altered, with mountains formed and worn down, coastlines reshaped, and entire ecosystems transformed. Additionally, the materials used by any hypothetical civilization might not have survived the test of time. Organic matter decays rapidly in geological terms, and even more durable materials like metals can corrode or be transformed over millions of years. This makes it extremely unlikely for any recognizable artifacts to have endured, leaving scientists with little tangible evidence to study or analyze in their search for ancient intelligent life. Plate tectonics plays a crucial role in shaping the Earth's surface and influencing the preservation of potential evidence, particularly in the field of paleontology and geology. The constant movement of tectonic plates can both reveal and conceal important clues about our planet's history. As tectonic plates shift and collide, they can uplift ancient seafloors, exposing fossils and rock formations that were once hidden beneath the waves. This process has allowed scientists to discover numerous marine fossils in mountainous regions, providing valuable insights into prehistoric life and past climates. However, the same forces that bring these treasures to the surface can also destroy or distort evidence. The intense pressure and heat generated by tectonic activity can metamorphose rocks, altering or erasing the fossils and geological markers they contain. Subduction zones, where one plate slides beneath another, can completely destroy potential evidence by melting it back into the Earth's mantle. Additionally, The fracturing and folding of rock layers during tectonic events can disrupt the chronological order of sedimentary deposits, making it challenging for scientists to accurately date and interpret the geological record. Despite these challenges, plate tectonics also creates new opportunities for preservation. Sedimentary basins formed by tectonic activity can accumulate layers of sediment, effectively burying and protecting fossils and other evidence from erosion and weathering. This process has led to the formation of rich fossil beds that have provided invaluable information about the history of life on Earth. Erosion is a powerful force that constantly reshapes our planet, and it plays a significant role in obscuring traces of ancient civilizations. Over time, wind, water, and ice gradually wear away the physical remnants of past societies, making it challenging for archaeologists to uncover and study these historical treasures. Water erosion, in particular, can be especially destructive to archaeological sites. Rivers change course, floods wash away artifacts, and rainfall slowly dissolves stone structures. In coastal areas, rising sea levels and storm surges can submerge entire cities, hiding them beneath the waves for centuries. Wind erosion is another factor that impacts the preservation of ancient sites. In desert regions, sandstorms can bury entire settlements under dunes, while also wearing away inscriptions and intricate details on stone monuments. This process can erase valuable information about past cultures and their ways of life. The effects of erosion are not limited to the destruction of physical structures. It also impacts the preservation of organic materials such as textiles, wooden objects, and human remains. As erosion exposes these delicate items to the elements, they can quickly decompose, taking with them crucial evidence about ancient civilizations and their practices. Changing sea levels have a profound effect on the search for ancient civilizations, transforming our understanding of human history and archaeological exploration. As global temperatures fluctuate over millennia, vast amounts of water shift between the oceans and land-based ice sheets, causing sea levels to rise and fall dramatically. During periods of lower sea levels, expansive coastal plains and land bridges emerged, providing habitable areas for ancient peoples. These now submerged landscapes hold invaluable clues about early human migrations and settlements. When sea levels rose again, these coastal communities were inundated, preserving a treasure trove of artifacts and structures beneath the waves. Marine archaeologists now employ advanced technologies like side-scan sonar and remotely operated vehicles to explore these underwater sites. Their discoveries range from sunken cities in the Mediterranean to prehistoric settlements in the North Sea, revealing complex societies that thrived along ancient coastlines. The impact of changing sea levels extends beyond submerged sites. As oceans encroach on modern coastlines, they expose previously hidden archaeological remains, creating a race against time for researchers to document these sites before they are lost to erosion. This dynamic interplay between land and sea continues to reshape our search for ancient civilizations, offering new challenges and opportunities for archaeological discovery. Extreme climate changes can have profound effects on the preservation of evidence from past civilizations. These shifts in environmental conditions can both destroy and protect archaeological remains, depending on the specific circumstances. In cases of increased aridity, organic materials like textiles, wood, and even human remains can be remarkably well preserved. The dry conditions inhibit the growth of bacteria and fungi that typically cause decay. This is why we have found such well-preserved mummies and artifacts in desert regions like Egypt and Peru. Conversely, extreme wet conditions can lead to the rapid deterioration of many materials. However, in some instances, waterlogged environments can create anaerobic conditions that actually preserve organic materials exceptionally well. This is particularly true in peat bogs, where we have discovered remarkably intact human bodies and wooden objects from thousands of years ago. Climate changes can also affect the visibility and accessibility of archaeological sites. Rising sea levels can submerge coastal settlements, while receding glaciers can reveal previously hidden artifacts and structures. Increased erosion due to more frequent storms or changes in vegetation cover can expose buried sites, but it can also destroy them if not quickly documented and protected. These dynamic processes highlight the urgency of archaeological work in the face of ongoing climate change. Fossilization is a remarkable process that transforms organic remains into mineralized versions of their former selves. This natural phenomenon occurs over incredibly long periods, often spanning millions of years. As an organism is buried beneath layers of sediment, its soft tissues typically decay, leaving behind only the hard parts such as bones, shells, or teeth. The surrounding sediment plays a crucial role in preservation. As water percolates through the layers, it carries dissolved minerals that slowly replace the original organic material in the remains. This mineral replacement, known as permineralization, creates a rock-like copy of the original structure, preserving its shape and sometimes even microscopic details. Different environments lead to varying types of fossilization. In some cases, the original material is completely dissolved, leaving behind a detailed mold or cast of the organism. Other times, the organic material is preserved through carbonization, where pressure compresses the remains into a thin, carbon-rich film. The fossilization process significantly impacts what we can learn from these ancient remnants. While it allows us to study the physical structure of long-extinct creatures, it often destroys delicate features and rarely preserves soft tissues. This selective preservation shapes our understanding of prehistoric life, providing a window into the past that is both invaluable and inherently limited. Exploring the deep ocean presents researchers with a unique set of challenges. The extreme pressure at great depths poses a significant obstacle, requiring specialized equipment that can withstand forces equivalent to several hundred atmospheres. This pressure not only affects research tools, but also limits the time humans can spend in submersibles, making extended observations difficult. Darkness is another major hurdle in deep ocean research. Sunlight penetrates only the upper layers of the ocean, leaving vast areas in perpetual darkness. Scientists must rely on artificial lighting, which can alter the behavior of light-sensitive organisms and potentially skew observations. This darkness also complicates navigation and mapping efforts, making it challenging to locate and revisit specific sites of interest. The sheer vastness of the deep ocean compounds these difficulties. Much of the seafloor remains unmapped and unexplored, with new species and geological features constantly being discovered. This immensity makes it challenging to conduct comprehensive surveys or to track changes in ecosystems over time. Additionally, the remote nature of many deep ocean locations increases the logistical complexity and cost of research expeditions. Technological limitations further constrain deep ocean research. While advances have been made in remotely operated vehicles and autonomous underwater vehicles, these tools still have limitations in terms of range, power supply, and data transmission. The harsh conditions of the deep sea can also cause equipment failures, potentially jeopardizing entire research missions and highlighting the need for robust, reliable technologies to unlock the secrets of this challenging environment. Earth's dynamic nature profoundly affects our ability to uncover evidence of ancient civilizations. The continuous recycling of the planet's crust through plate tectonics, erosion, and deposition constantly reshapes the surface, erasing or burying traces of past societies. Tectonic activity plays a significant role in this process. As continental plates collide, subduct, or separate, entire landscapes can be altered. Ancient coastal settlements might now lie beneath the waves, while once thriving inland cities could be buried under mountains. This constant movement makes it challenging for archaeologists to locate and study sites that existed thousands of years ago. Erosion and sedimentation further complicate the search. Wind and water gradually wear away exposed structures and artifacts, while simultaneously depositing layers of soil and debris over others. In some cases, entire cities have been hidden beneath sand dunes or jungle growth, only to be rediscovered centuries later. These geological processes create a race against time for archaeologists. As they work to uncover and preserve ancient sites, the Earth continues its relentless cycle of destruction and renewal. This ongoing transformation of the planet's surface serves as a reminder of the transient nature of human civilization in the face of Earth's powerful geological forces. Current dating methods face significant challenges when examining extremely old artifacts, particularly those beyond several 100,000 years. Carbon-14 dating, a commonly used technique, becomes increasingly unreliable for objects older than 50,000 years due to the decay of carbon-14 isotopes. This limitation forces scientists to rely on other methods for dating ancient artifacts. Potassium-argon dating and uranium-lead dating can measure much older timescales, but they require specific minerals to be present in the artifact or surrounding material. These methods also become less precise with extremely old samples, as the accumulation of daughter isotopes becomes more difficult to measure accurately over vast time periods. Another challenge lies in contamination. Over millions of years, artifacts can be exposed to various environmental factors that alter their chemical composition. This contamination can lead to inaccurate age estimates, as the original isotopic ratios may have been disturbed. Scientists must employ rigorous cleaning and preparation techniques to minimize these effects, but some level of uncertainty always remains. For the oldest artifacts, such as those from the early Earth or even meteorites, the limitations of current dating methods become even more pronounced. The scarcity of suitable samples, the potential for multiple heating and cooling events, and the extreme timescales involved all contribute to increased uncertainty in age determinations. These challenges underscore the ongoing need for refinement and development of new dating techniques to push the boundaries of our understanding of ancient history. Current human activities pose significant challenges to the search for ancient civilizations. As our modern world expands and develops, we inadvertently destroy or obscure evidence of past societies. Urban growth and infrastructure projects often lead to the bulldozing of potential archaeological sites, burying or destroying valuable artifacts and structures before they can be properly studied. Agriculture also plays a role in this interference. As farmers plow fields and introduce new irrigation systems, they can disturb or damage buried remains. The use of chemical fertilizers and pesticides can alter the chemical composition of the soil, making it more difficult for archaeologists to accurately date organic materials found at these sites. Climate change, largely driven by human activities, is another major factor. Rising sea levels threaten coastal archaeological sites, while increased flooding and erosion can damage or completely wash away important historical locations. Conversely, desertification in some regions can bury sites under sand, making them harder to locate and excavate. Lastly, looting and illegal artifact trafficking continue to be significant problems. The global demand for ancient artifacts fuels unauthorized excavations, which often destroy the contextual information crucial for understanding these civilizations. This illegal activity not only removes valuable pieces from their original locations, but also damages the integrity of archaeological sites, making it more challenging for researchers to piece together the puzzle of ancient cultures. The discovery of a 100-million-year-old civilization would fundamentally reshape our understanding of human history and challenge everything we know about the evolution of intelligent life on Earth. Such a finding would be utterly revolutionary, as it would predate the evolution of modern humans by tens of millions of years. This hypothetical ancient civilization would have existed during the Mid-Cretaceous period, a time when dinosaurs still roamed the Earth and flowering plants were just beginning to diversify. The implications of such a discovery would extend far beyond archaeology and anthropology, impacting our understanding of biology, geology, and even the nature of intelligence itself. One of the most profound consequences would be the realization that humans are not the first intelligent species to inhabit Earth. This would force us to reconsider our place in the universe and the potential for intelligent life to arise in various forms. It would also raise questions about why this civilization disappeared and whether there could have been multiple advanced species throughout Earth's history that we have yet to discover. Furthermore, such a finding would necessitate a complete re-examination of the fossil record and our methods of dating ancient artifacts. It would challenge our current models of planetary development and potentially provide insights into long-term climate patterns and geological processes over vast timescales. The technological and cultural achievements of this ancient civilization could also offer valuable lessons for our own society, potentially revolutionizing our approach to sustainable living and long-term survival as a species. The discovery of life on other planets would profoundly impact our understanding of evolution. It would provide a unique opportunity to study how life develops in different environments, potentially revealing new pathways of adaptation and survival. If the alien life forms share similar biochemical foundations with Earth life, such as DNA or RNA, it would suggest that certain aspects of evolution might be universal. This could indicate that life tends to follow specific patterns regardless of where it emerges, reinforcing some of our existing theories. However, if the extraterrestrial organisms are fundamentally different from Earth life, it would challenge our current models of evolution. We might need to reconsider our assumptions about the necessary conditions for life and the processes that drive evolutionary change. This could lead to a more expansive view of how life can adapt and thrive in diverse cosmic environments. Furthermore, studying alien life could help us understand the role of convergent evolution on a galactic scale. We might discover similar traits or behaviors that evolved independently on different planets, providing insights into the universal challenges of survival and the solutions life develops to overcome them. The discovery of extraterrestrial life would fundamentally reshape our understanding of the universe and our place within it. This revelation would have far-reaching implications across multiple scientific disciplines, from biology to astronomy. It would challenge our assumptions about the uniqueness of life on Earth and force us to reconsider the potential for life to arise and thrive in diverse environments. In the realm of biology, such a discovery would provide new insights into the origins and evolution of life. It could reveal alternative biochemistries and evolutionary pathways, expanding our understanding of what constitutes life and how it can adapt to different conditions. This knowledge could revolutionize fields such as astrobiology and exobiology, opening up new avenues for research and exploration. Philosophically, the confirmation of extraterrestrial life would prompt a re-evaluation of humanity's significance in the cosmos. It would challenge long-held beliefs about our uniqueness and potentially impact religious and cultural perspectives. The discovery might foster a sense of cosmic unity, as we recognize our shared status as living beings in a vast universe. Moreover, this revelation would likely accelerate our efforts in space exploration and the search for intelligent life. It would drive technological advancements in interstellar communication and propulsion systems as humanity seeks to reach out and potentially make contact with our cosmic neighbors. The discovery of extraterrestrial life would mark a new chapter in human history, forever changing how we view ourselves and our place in the universe. Discovering the technology of an ancient advanced civilization would be a monumental find, offering insights that could revolutionize our understanding of history and science. Such a discovery might reveal innovative approaches to energy production, potentially unveiling clean, efficient methods that could address our current environmental challenges. Their technology could demonstrate advanced materials science, showing us new ways to create stronger, lighter, or more durable substances. The medical knowledge of an advanced ancient civilization might be particularly valuable. We could uncover treatments for diseases that still plague us today, or learn new techniques for extending human longevity. Their understanding of the human body and mind might far surpass our own, leading to breakthroughs in neuroscience and psychology. In the realm of space exploration, an ancient civilization's technology could provide us with improved propulsion systems or methods for sustaining life in hostile environments. This knowledge could accelerate our efforts to explore and potentially colonize other planets. Additionally, their computational systems might introduce us to entirely new paradigms in information processing and storage, pushing the boundaries of our current digital capabilities. Perhaps most intriguingly, we might learn how this civilization managed its resources and societal structures to achieve such advanced technology. This could offer valuable lessons for our own global challenges, potentially showing us sustainable ways to balance technological progress with environmental stewardship and social harmony. The implications of such a discovery would extend far beyond technology, potentially reshaping our entire worldview and our place in the cosmos. The discovery of extraterrestrial life would profoundly reshape our approach to global challenges. It would unite humanity in a shared sense of cosmic perspective, potentially diminishing the perceived importance of national borders and conflicts. This newfound unity could foster increased international cooperation on pressing issues like climate change and resource management. Our technological capabilities would likely advance rapidly as we strive to communicate with and potentially visit these alien life forms. This accelerated progress could yield innovative solutions to energy production, environmental protection, and space exploration. The knowledge gained from studying alien biology and ecosystems might revolutionize medicine, agriculture, and our understanding of Earth's biodiversity. Moreover, encountering an advanced alien civilization could provide us with new models for sustainable development and social organization. We might learn more efficient ways to manage our resources, govern our societies, or harness clean energy. This influx of new ideas and technologies could help us address long-standing issues like poverty, disease, and environmental degradation. However, the discovery might also present new challenges. We would need to reevaluate our place in the universe and possibly confront existential questions about our significance. This could lead to societal upheaval as we grapple with these profound implications. Nonetheless, the overall impact would likely drive us toward a more unified, technologically advanced, and outward-looking global civilization. The discovery of extraterrestrial life would raise profound ethical questions for humanity. One key consideration would be how to interact with alien life forms without causing harm or disrupting their natural development. We would need to carefully weigh the potential benefits of contact against risks of contamination or unintended consequences. Another crucial ethical issue would be whether humans have the right to exploit or colonize alien worlds that harbor life. Many would argue that all life deserves protection and respect, regardless of its origin. However, others might contend that human needs should take priority, especially if alien life is microbial or primitive. The question of information sharing would also be ethically complex. How much should be disclosed to the public about an alien discovery? While transparency is important, revealing too much could lead to panic or misuse of knowledge. Balancing scientific openness with responsible communication would be challenging. Ultimately, encountering alien life would test our ethical frameworks and force us to grapple with fundamental questions about the value of life, our place in the cosmos, and our responsibilities as an intelligent species. It would likely spur new fields of ethics and philosophy to address these unprecedented moral dilemmas. The discovery of life beyond Earth would revolutionize our search for extraterrestrial life, dramatically expanding our understanding of where and how life can exist. It would provide crucial data about the conditions necessary for life to emerge and thrive, potentially revealing new environments we had not previously considered habitable. This knowledge would allow us to refine our search techniques and target specific types of planets or moons that share characteristics with the world where life was found. For instance, if we discovered microbial life in the subsurface oceans of an icy moon, we would prioritize similar environments in our future explorations. Moreover, such a discovery would likely accelerate the development of new technologies and methods for detecting signs of life. We might create more sensitive instruments to detect biosignatures or devise innovative ways to study potential habitats remotely. The confirmation that we are not alone in the universe would also likely increase public and scientific interest in the search, potentially leading to increased funding and resources for astrobiology and space exploration programs. Ultimately, finding life elsewhere would transform our perspective on the prevalence of life in the cosmos. It would suggest that life might be more common than we currently believe, encouraging us to broaden our search and reconsider our assumptions about the conditions required for life to exist. The exploration and understanding of our universe have profound implications for religious and cultural beliefs around the world. As scientific discoveries continue to unveil the vastness and complexity of the cosmos, many people find themselves re-evaluating long-held beliefs about creation, our place in the universe, and the nature of existence itself. For some, these scientific revelations strengthen their faith, seeing the intricate workings of the universe as evidence of divine design. Others may find their traditional beliefs challenged, leading to a reinterpretation of religious texts or a shift towards more metaphorical understandings of creation stories. In many cultures, the concept of extraterrestrial life is becoming more accepted, potentially altering views on humanity's uniqueness. This shift in perspective could foster a more unified global outlook, as people recognize our shared place in the cosmos. Moreover, the awe-inspiring scale of the universe often instills a sense of humility and interconnectedness. This cosmic perspective can influence ethical considerations, environmental awareness, and even geopolitical attitudes, as borders and differences seem less significant when viewed against the backdrop of our vast universe. The discovery of extraterrestrial intelligence would profoundly reshape our understanding of intelligence and consciousness. It would provide an entirely new context for studying cognitive processes, potentially revealing alternative forms of problem-solving, communication, and self-awareness. By comparing our intelligence to that of an alien species, we could gain insights into the fundamental nature of consciousness. We might discover that intelligence can arise from vastly different biological or even non-biological substrates, challenging our Earth-centric notions of what constitutes a thinking being. This discovery could also shed light on the evolution of intelligence. We might find that certain cognitive traits are universal, suggesting they are inherent to the development of advanced problem-solving abilities. Conversely, we could encounter forms of intelligence so foreign to us that they force us to expand our very definition of what it means to be conscious. Furthermore, contact with an alien intelligence could provide new perspectives on the relationship between technology and consciousness. We might learn how other civilizations have integrated advanced technology with their cognitive processes, potentially offering glimpses into the future of human-machine interfaces or artificial intelligence. The discovery of ancient extraterrestrial civilizations would profoundly reshape our understanding of the rise and fall of civilizations, both on Earth and across the cosmos. This revelation would force us to reconsider the factors that contribute to the longevity and collapse of advanced societies on a universal scale. One key implication would be the recognition that civilizations can indeed survive for immense periods, potentially millions or even billions of years. This would challenge our current perceptions of societal lifespans and suggest that with the right conditions and adaptations, intelligent species can persist for extraordinary durations. However, the existence of extinct alien civilizations would also underscore the fragility of advanced societies. It would highlight that even highly developed cultures can succumb to various catastrophic events or gradual declines. This realization might prompt us to identify common patterns or challenges that civilizations face across the universe, such as resource depletion, environmental changes, or technological risks. Furthermore, studying the remnants of these ancient alien cultures could provide invaluable insights into the potential trajectories of our own civilization. By examining their technological artifacts, social structures, and possible reasons for collapse, we might gain crucial knowledge to help navigate our own long-term survival and development as a species. Many anomalies, often cited as evidence for ancient advanced civilizations, can be explained through a combination of natural geological processes, the ingenuity of ancient peoples, and misinterpretations of archaeological findings. One common example is the precise stone cutting and fitting seen in structures like those at Pumapunku in Bolivia. While some claim these as proof of advanced technology, archaeologists have demonstrated that these feats were achievable using Bronze Age tools and techniques. The ancient builders likely used a combination of stone hammers, bronze chisels, and abrasive sand to shape the stones, along with sophisticated surveying and engineering knowledge. Another frequently cited anomaly is the existence of submerged structures, such as those off the coast of Japan or in the Mediterranean. While these are sometimes attributed to lost civilizations like Atlantis, most can be explained by known geological processes. Sea levels have fluctuated significantly over millennia, submerging once coastal settlements. Additionally, some underwater formations initially thought to be artificial have been revealed as natural geological features upon closer examination. Unusual artifacts, like the Antikythera mechanism or Baghdad batteries, are often presented as evidence of advanced ancient technology. However, these items typically represent the pinnacle of achievement for their time rather than anachronistic technology. The Antikythera mechanism, for instance, while impressively complex, aligns with the astronomical knowledge and mechanical skills of ancient Greece. Similarly, the so-called Baghdad batteries likely served religious or medicinal purposes rather than being early electrical devices. Skeptics approach claims related to the Silurian hypothesis with a combination of scientific rigor and critical thinking. The Silurian hypothesis proposes that an advanced civilization might have existed on Earth millions of years ago, leaving little to no trace of their presence. Skeptics examine this idea through the lens of available evidence and established scientific principles. One key aspect skeptics consider is the geological record. They point out that human activities have left clear markers in the Earth's strata, such as plastics, radioactive isotopes, and other pollutants. The absence of similar markers from millions of years ago suggests that no comparable civilization existed in the deep past. Skeptics also emphasize the importance of extraordinary evidence for extraordinary claims. They argue that while the Silurian hypothesis is an interesting thought experiment, it lacks concrete evidence to support its assertions. Instead, they encourage focusing on well-established scientific theories about Earth's history and the evolution of life. Furthermore, skeptics highlight the need for testable hypotheses. They challenge proponents of the Silurian hypothesis to provide specific predictions that could be verified through geological or paleontological research, rather than relying on speculative scenarios or gaps in our knowledge of Earth's past. Confirmation bias significantly influences how we interpret potential evidence, often leading us to favor information that supports our existing beliefs while dismissing contradictory data. This cognitive tendency can profoundly impact scientific research and our understanding of the universe. In the realm of cosmology and astronomy, confirmation bias can shape how scientists and the public alike perceive new discoveries. For instance, when searching for signs of extraterrestrial life, researchers might be more inclined to interpret ambiguous signals as potential evidence of alien civilizations if they already believe such life exists. Conversely, skeptics might quickly dismiss the same data, attributing it to natural phenomena or instrumental errors. This bias can also affect how we interpret evidence related to fundamental questions about the universe. When examining data about dark matter or dark energy, scientists must be vigilant against the tendency to favor observations that align with their preferred theories. The history of science is replete with examples where confirmation bias delayed the acceptance of groundbreaking ideas, from heliocentrism to plate tectonics. To combat confirmation bias, the scientific method emphasizes rigorous testing, peer review, and the importance of reproducibility. By actively seeking to disprove hypotheses and welcoming scrutiny from colleagues, researchers strive to minimize the impact of personal biases on their work. This approach helps ensure that our understanding of the cosmos is built on solid evidence rather than preconceived notions. Scientists employ rigorous methods to distinguish genuine evidence from pseudoscientific claims. At the core of this process is the scientific method, which involves forming hypotheses, conducting experiments, and analyzing results. This systematic approach allows researchers to test ideas and theories against observable reality. One key aspect of scientific inquiry is peer review. When scientists make a discovery or propose a new theory, they submit their work to other experts in the field for scrutiny. These peers examine the methodology, data, and conclusions, looking for potential flaws or alternative explanations. This process helps filter out weak or unsupported claims before they reach wider audiences. Reproducibility is another crucial factor. For a scientific claim to be considered valid, other researchers should be able to replicate the results independently. This requirement helps weed out flukes, errors, and deliberate fabrications. In contrast, pseudoscientific claims often rely on anecdotes, personal experiences, or results that cannot be consistently reproduced. Scientists also place great importance on evidence that can be measured and quantified. They use statistical analysis to determine if results are significant or merely due to chance. Pseudoscience, on the other hand, often relies on vague, untestable claims or cherry-picked data that supports a predetermined conclusion. By adhering to these principles, scientists can separate reliable evidence from unfounded assertions, ensuring that our understanding of the universe is based on solid, verifiable facts. The Silurian hypothesis, which proposes the possibility of advanced civilizations existing on Earth long before humans, is often misunderstood. One common misconception is that the hypothesis suggests the existence of reptilian humanoids, similar to the fictional Silurians from Doctor Who. In reality, the hypothesis does not specify any particular type of species or civilization. Another misconception is that the Silurian hypothesis claims definitive proof of ancient advanced civilizations. This is not the case. The hypothesis merely explores the potential for such civilizations to have existed and questions our ability to detect them in the geological record after millions of years. Some people mistakenly believe that the hypothesis contradicts established scientific understanding of Earth's history. However, it actually encourages scientists to consider how we might recognize the long-term impact of industrial civilizations in the geological record, including our own. Lastly, there is a misconception that the Silurian hypothesis supports pseudo-scientific claims about lost advanced civilizations like Atlantis. In truth, the hypothesis is a thought experiment within the scientific community aimed at understanding the limits of our knowledge about Earth's deep history and the potential markers of technological societies in the geological record. Researchers investigating extraordinary claims must walk a fine line between open-mindedness and scientific skepticism. This balance is crucial for maintaining the integrity of scientific inquiry while remaining receptive to potentially groundbreaking discoveries. Scientists approach these claims by first acknowledging that our understanding of the universe is incomplete. They recognize that what seems impossible today might be proven true tomorrow. However, they also understand that extraordinary claims require extraordinary evidence. This principle, popularized by Carl Sagan, forms the foundation of their investigative approach. The scientific method serves as the cornerstone for evaluating these claims. Researchers design experiments that can be replicated, collect data objectively, and analyze results without bias. They actively seek alternative explanations and attempt to disprove their own hypotheses. This rigorous process helps filter out false positives and ensures that any positive findings are robust and reliable. Collaboration and peer review play vital roles in maintaining this balance. By sharing their work with colleagues and inviting scrutiny, researchers benefit from diverse perspectives and expertise. This collective approach helps identify potential flaws in methodology or interpretation, ultimately strengthening the validity of their findings. Through this careful balance of openness and rigor, scientists can explore new frontiers while upholding the highest standards of scientific inquiry. Scientists employ rigorous methods to assess extraordinary claims about ancient civilizations. They rely on multiple lines of evidence, including archaeological findings, historical records, and scientific analysis. Physical artifacts are carefully examined and dated using techniques such as radiocarbon dating and thermoluminescence. Researchers also analyze written documents, inscriptions, and oral traditions, cross-referencing them with known historical events and cultural practices. Interdisciplinary collaboration is crucial in evaluating extraordinary claims. Archaeologists work alongside historians, linguists, geologists, and other specialists to build a comprehensive understanding of ancient societies. They consider the context of discoveries, examining how new information fits within existing knowledge of a civilization's technology, social structure, and cultural norms. Reproducibility and peer review play vital roles in the scientific process. Extraordinary claims must be supported by evidence that can be independently verified by other researchers. Scientists scrutinize methodologies, data collection, and interpretations, challenging assumptions and seeking alternative explanations. This rigorous evaluation helps separate fact from speculation and ensures that new theories about ancient civilizations are based on solid evidence. Ultimately, scientists remain open to new discoveries while maintaining a healthy skepticism. They weigh the plausibility of claims against known historical and scientific principles, always seeking the most logical and well-supported explanations for archaeological findings and historical mysteries. The principle of Occam's razor, which favors simpler explanations over more complex ones, has interesting implications for the Silurian hypothesis. This hypothesis proposes that an advanced civilization might have existed on Earth millions of years ago, leaving little to no trace of their presence. When applying Occam's razor to this idea, we must consider which explanation requires fewer assumptions. The conventional understanding of Earth's history, supported by extensive geological and paleontological evidence, suggests that complex civilizations only emerged within the last few thousand years. This view aligns with our current knowledge of evolutionary processes and the fossil record. The Silurian hypothesis, on the other hand, requires us to assume the existence of an advanced civilization that somehow left no clear evidence of its presence. It also necessitates explanations for how this civilization arose, flourished, and disappeared without leaving easily detectable traces in the geological record. Given these considerations, Occam's razor would generally favor the conventional view of Earth's history. However, it's important to note that while Occam's razor is a useful tool in scientific thinking, it does not prove or disprove hypotheses. The principle simply suggests that simpler explanations are often more likely to be correct, all else being equal. Throughout history, numerous claims about ancient advanced civilizations have captured the public imagination, only to be debunked by rigorous scientific investigation. One prominent example is the myth of Atlantis, a supposedly advanced island nation described by Plato. Despite centuries of searching, no evidence of its existence has ever been found, and most scholars now interpret it as a fictional allegory. Another debunked claim involves the idea that the Egyptian pyramids were built by aliens or a lost advanced civilization. In reality, extensive archaeological evidence shows that ancient Egyptians constructed these monuments using sophisticated but entirely human engineering techniques. Similarly, claims that the Nazca lines in Peru were created as landing strips for extraterrestrial spacecraft have been thoroughly disproven, with research revealing they were made by pre-Columbian cultures for religious and astronomical purposes. The notion of a technologically advanced civilization in ancient India, often cited in relation to descriptions of flying machines in Sanskrit texts, has also been debunked. While these texts contain imaginative descriptions, there is no archaeological evidence to support the existence of such technology. Likewise, claims about crystal skulls being artifacts from advanced ancient American cultures have been shown to be false, with modern analysis revealing they were created in the 19th and 20th centuries. These examples highlight the importance of scientific scrutiny in separating fact from fiction when it comes to claims about ancient civilizations. While the idea of lost advanced societies is alluring, the evidence consistently points to the remarkable but entirely human achievements of our ancestors. Scientists approach public misconceptions about the Silurian hypothesis with a combination of education, clarification, and emphasis on the scientific method. The Silurian hypothesis, which suggests the possibility of an advanced civilization existing on Earth millions of years ago, often sparks curiosity and speculation among the public. Researchers stress that this hypothesis is a thought experiment rather than a widely accepted scientific theory. They explain that while it is an interesting concept to consider, there is currently no concrete evidence supporting the existence of such an ancient, technologically advanced society. Scientists emphasize the importance of distinguishing between speculation and empirical evidence. To address misconceptions, experts often highlight the challenges of finding preserved evidence from millions of years ago. They explain how geological processes and time would likely erase most traces of an ancient civilization, making it difficult to prove or disprove the hypothesis definitively. This discussion helps the public understand the complexities involved in studying Earth's distant past. Scientists also use the Silurian hypothesis as an opportunity to educate the public about actual geological and paleontological discoveries. By showcasing real findings from the Silurian period and other ancient eras, they redirect interest towards the fascinating realities of Earth's history, while maintaining a clear distinction between established facts and speculative ideas. Archaeologists employ a range of sophisticated techniques to uncover evidence of ancient civilizations. Ground-penetrating radar allows researchers to detect buried structures and artifacts without disturbing the soil. This technology sends radar pulses into the ground, creating detailed images of what lies beneath the surface. Satellite imagery has revolutionized archaeological surveys, enabling scientists to identify potential sites from space. These images can reveal subtle changes in vegetation or soil color that indicate the presence of buried ruins. LIDAR, which uses laser pulses to create three-dimensional maps, has proven particularly effective in densely forested areas, uncovering hidden structures obscured by vegetation. In the field, archaeologists use careful excavation methods to unearth artifacts and structures. They meticulously record the position and context of each find, often using photogrammetry to create detailed three-dimensional models. Radiocarbon dating and other scientific techniques help determine the age of organic materials, while thermoluminescence dating can be used for ceramics and other inorganic objects. Interdisciplinary collaboration is crucial in modern archaeology. Geneticists analyze ancient DNA to trace population movements and relationships. Geologists study soil composition and stratigraphy to understand site formation processes. Paleobotanists examine plant remains to reconstruct ancient environments and diets. Together, these diverse methods paint a comprehensive picture of ancient civilizations, revealing their technologies, social structures, and ways of life. Archaeologists face unique challenges when searching for evidence of extremely old civilizations. These ancient societies, often dating back tens of thousands of years, require specialized approaches to uncover their secrets. One key adaptation is the use of advanced dating techniques. Radiocarbon dating, while useful for more recent history, becomes less reliable for extremely old artifacts. Instead, archaeologists turn to methods like thermoluminescence, which can date pottery and other fired clay objects, or optically stimulated luminescence, used to determine when sediments were last exposed to sunlight. These techniques allow researchers to probe much further into the past. The search for ancient civilizations also requires a shift in focus. Rather than looking for large structures or written records, archaeologists often seek out more subtle clues. They examine changes in soil composition, search for microscopic plant remains, and analyze ancient pollen samples to understand how human activity altered the environment over time. This approach helps reveal the presence of early societies that may not have left behind monumental architecture. Collaboration with other scientific fields has become increasingly important. Archaeologists work closely with geologists to understand how landscapes have changed over millennia, and with geneticists to analyze ancient DNA found in bones or teeth. These interdisciplinary efforts provide a more comprehensive picture of ancient civilizations, helping to fill in gaps where physical evidence is scarce. Satellite imagery has revolutionized archaeological research, offering a powerful tool for identifying potential sites of ancient habitation. This technology allows archaeologists to survey vast areas of land from above, revealing features and patterns that are often invisible from the ground. One of the key advantages of satellite imagery is its ability to detect subtle changes in vegetation and soil composition. Ancient settlements often leave lasting impacts on the landscape, altering the growth patterns of plants and the chemical makeup of the soil. These changes can create distinctive marks known as crop marks or soil marks, which are visible from space but may be imperceptible at ground level. Satellite imagery also enables researchers to identify geometric shapes and patterns that could indicate human-made structures. Ancient walls, roads, and building foundations often create regular shapes that stand out against the natural landscape. Advanced imaging techniques, such as infrared and multispectral analysis, can reveal even more details, allowing archaeologists to see through dense vegetation or detect buried structures. Furthermore, satellite technology helps archaeologists track changes in potential sites over time. By comparing images taken at different periods, researchers can monitor the effects of erosion, urban development, and other factors that might threaten ancient sites. This information is crucial for prioritizing excavation efforts and developing conservation strategies to protect valuable archaeological resources. Researchers employ core samples as time capsules to peer into Earth's ancient history. These cylindrical sections of rock or sediment, extracted from deep within the Earth or ocean floor, contain layers that accumulate over millions of years. Each layer holds valuable clues about past climates, environments, and life forms. By analyzing the chemical composition, fossil content, and physical properties of these layers, scientists can reconstruct past conditions on our planet. For instance, examining the ratio of oxygen isotopes in marine sediment cores provides insights into ancient ocean temperatures and global ice volume. Pollen grains preserved in lake sediments reveal information about past vegetation and climate changes. Core samples also allow researchers to study past atmospheric conditions. Tiny air bubbles trapped in ice cores from Antarctica and Greenland serve as direct samples of ancient atmospheres, offering data on greenhouse gas levels from hundreds of thousands of years ago. This information is crucial for understanding long-term climate trends and the potential impacts of current climate change. The study of core samples has revolutionized our understanding of Earth's history. It has provided evidence for major events like mass extinctions, ice ages, and rapid climate shifts, helping scientists piece together the complex story of our planet's past and informing predictions about its future. Paleoclimatology, the study of past climates, offers valuable insights into the environmental conditions that may have influenced the rise and fall of ancient civilizations. By analyzing various climate proxies such as ice cores, tree rings, and sediment samples, scientists can reconstruct temperature patterns, rainfall levels, and other climatic factors from thousands of years ago. This information helps us understand how ancient societies might have adapted to their environments and how climate changes could have impacted their development. For instance, paleoclimatological data has revealed periods of prolonged drought in the Middle East that coincide with the collapse of several Bronze Age civilizations. Similarly, evidence of climate shifts in Central America has been linked to the decline of Maya city-states. Paleoclimatology also allows us to identify periods of favorable climate conditions that could have supported the growth of complex societies. Stable and mild climates with consistent rainfall patterns might have enabled the development of agriculture, leading to food surpluses and population growth, key factors in the emergence of early civilizations. Moreover, this field of study can hint at the potential existence of yet undiscovered ancient settlements. By identifying regions that experienced favorable climate conditions in the past, archaeologists can focus their efforts on areas more likely to have supported human habitation and complex social structures. Thus, paleoclimatology serves as a crucial tool in our quest to uncover and understand the civilizations of our distant past. Scientists harness the power of computer modeling to explore and test hypotheses about ancient civilizations in remarkable ways. These digital tools allow researchers to recreate environments, simulate social interactions, and analyze complex datasets, providing valuable insights into the past. One key application of computer modeling is in reconstructing ancient landscapes. By combining geological data, climate information, and archaeological findings, scientists can create virtual representations of how an area might have looked thousands of years ago. These models help researchers understand how ancient peoples interacted with their environment, where they might have settled, and how changes in climate or geography could have influenced their societies. Computer simulations also play a crucial role in testing theories about social structures and decision-making processes in ancient civilizations. Researchers can input known data about population sizes, resource availability, and cultural practices into these models. They then run simulations to see how different scenarios might have played out over time. This approach allows scientists to test hypotheses about everything from agricultural practices to the spread of innovations across ancient societies. Furthermore, computer modeling aids in the analysis of artifacts and architectural remains. By creating three-dimensional digital reconstructions of ancient buildings or cities, researchers can study their design, layout, and potential uses in ways that would be impossible with physical remains alone. These models can even simulate how structures might have responded to natural disasters, helping scientists understand the challenges faced by ancient civilizations and how they adapted to their environments. Interdisciplinary collaboration is crucial in exploring the intriguing Silurian hypothesis, which proposes the possibility of advanced civilizations existing on Earth millions of years before humans. This concept requires expertise from diverse fields to thoroughly investigate its implications and potential evidence. Geologists and paleontologists play a vital role in examining the rock record for any anomalous features that could indicate past technological activity. They search for unusual chemical signatures, unexplained geological formations, or artifacts that might have survived the ravages of time. Climatologists contribute by analyzing long-term climate data for patterns that could suggest large-scale industrial activity in the distant past. Biologists and evolutionary scientists lend their knowledge to consider how an advanced species might have evolved and what traces they could have left in the fossil record. Astronomers and astrophysicists bring valuable insights into how we might detect signs of ancient civilizations on other planets, which can inform our search on Earth. Archaeologists and anthropologists offer expertise in recognizing patterns of civilization, development, and the types of evidence that tend to persist over time. Computer scientists and data analysts are essential for processing vast amounts of information from various sources, helping to identify patterns or anomalies that human researchers might overlook. This collaborative approach ensures a comprehensive examination of the Silurian hypothesis, combining multiple perspectives to explore one of the most fascinating questions about our planet's history. Isotope analysis has become a powerful tool in the archaeologist's arsenal, helping unravel the mysteries of ancient civilizations. This technique allows researchers to examine the chemical composition of artifacts, human remains, and even soil samples to gain insights into past societies. When studying human remains, isotope analysis of bones and teeth can reveal details about an individual's diet, migration patterns, and living conditions. Different foods leave distinct isotopic signatures in the body, allowing scientists to determine if ancient people primarily consumed plants, meat, or seafood. This information sheds light on agricultural practices, hunting habits, and trade networks of long-lost cultures. Researchers also use isotope analysis to trace the origins of ancient artifacts. By examining the isotopic composition of materials like pottery, metals, and gemstones, scientists can identify the geological sources of these items. This helps map trade routes and connections between different civilizations, revealing complex networks of cultural exchange that spanned vast distances. Furthermore, isotope analysis of soil and plant remains can provide insights into past climates and environmental conditions. This information helps archaeologists understand how ancient civilizations adapted to changing environments and how climate shifts might have influenced the rise and fall of different cultures. By combining isotope analysis with other archaeological methods, researchers continue to piece together a more comprehensive picture of our ancient past. Archaeologists are harnessing cutting-edge technologies to uncover the secrets of ancient civilizations. One groundbreaking method is light detection and ranging, or LiDAR, which uses laser pulses to create detailed three-dimensional maps of landscapes. This technology can penetrate dense vegetation, revealing hidden structures and entire lost cities beneath the jungle canopy. Satellite imagery analysis has also revolutionized archaeological prospection. Advanced algorithms can now detect subtle patterns in the landscape that indicate buried structures or long-lost roadways. This allows researchers to identify potential sites of interest across vast areas without setting foot on the ground. Underwater archaeology has seen significant advancements with the development of autonomous underwater vehicles. These robots can explore shipwrecks and submerged ruins at depths unreachable by human divers, capturing high-resolution images and even collecting samples for analysis. DNA analysis is providing new insights into ancient populations. By extracting genetic material from archaeological remains, scientists can trace migration patterns, understand familial relationships, and even identify specific individuals from historical records. This molecular approach is rewriting our understanding of human history and the interconnectedness of ancient cultures. Scientists employ rigorous methods to maintain the integrity of their research, especially when dealing with controversial theories. Peer review stands as a cornerstone of scientific integrity, where experts in the field critically examine the research before publication. This process helps identify potential flaws in methodology, analysis, or interpretation. Replication is another crucial aspect of scientific integrity. Other researchers attempt to reproduce the results independently, validating the original findings or revealing inconsistencies. This practice helps weed out false positives and strengthens confidence in genuine discoveries. Transparency plays a vital role in ensuring scientific integrity. Researchers are expected to fully disclose their methods, data, and potential conflicts of interest. This openness allows others to scrutinize the work thoroughly and build upon it. Additionally, many scientific journals now require data sharing, enabling other scientists to reanalyze the raw information. Collaboration across different institutions and countries also bolsters the integrity of scientific findings. By involving diverse perspectives and expertise, researchers can minimize bias and enhance the robustness of their conclusions. This approach is particularly valuable when investigating controversial theories, as it helps ensure that findings are based on solid evidence rather than preconceived notions or individual agendas. Imagining the technological capabilities of a civilization from 100 million years ago challenges our understanding of both cosmic and evolutionary timescales. On Earth, this period coincides with the middle of the Cretaceous era, when dinosaurs still roamed the planet and mammals were small, nocturnal creatures. However, for a hypothetical alien civilization, the story could be vastly different. Given sufficient time and the right conditions, an advanced species might have developed technology far beyond our current capabilities. They could have mastered interstellar travel, harnessed the energy of entire stars, or even manipulated the fabric of spacetime itself. Such a civilization might have created vast networks of self-replicating machines, spreading their influence across multiple galaxies. However, it is also possible that even an advanced civilization from that time might have faced extinction or technological regression due to cosmic events like gamma-ray bursts, nearby supernovae, or collisions with other celestial bodies. The challenges of long-term survival on cosmic timescales are immense and largely unknown to us. Ultimately, the level of technology achieved by an ancient civilization remains a subject of speculation. It serves as a reminder of the vast temporal and spatial scales of the universe and the potential for technological advancement over immense periods of time. Intelligent beings from 100 million years ago would likely have evolved under vastly different conditions than humans, resulting in significant biological differences. Their physiology would be adapted to the environment of that era, which had higher carbon dioxide levels and warmer global temperatures. These ancient beings might have developed more efficient respiratory systems to cope with the different atmospheric composition. Their cardiovascular systems could be more robust to handle the increased temperatures. Their skin might have additional protection against the stronger ultraviolet radiation that reached the surface before the ozone layer fully formed. Their sensory organs could be quite different from ours. They might have developed enhanced vision to see in different light conditions, or even the ability to perceive wavelengths beyond our visual spectrum. Their auditory system could be adapted to detect sounds in different frequency ranges, possibly allowing them to communicate over long distances. Given the different available food sources, their digestive systems would likely be adapted to process the flora and fauna of that time. They might have specialized organs or symbiotic relationships with microorganisms to break down cellulose or other complex molecules that were prevalent in their diet. Their brains could have evolved different structures, potentially leading to unique cognitive abilities or ways of processing information compared to modern humans. A civilization as ancient as the one we're exploring would likely have developed complex social structures over its long history. Given their advanced technological capabilities, we might expect a highly organized society with specialized roles and intricate hierarchies. One possibility is a meritocratic system where individuals are assigned positions based on their abilities and contributions to society. This could lead to a stratified structure with different classes or castes responsible for various aspects of their civilization, such as scientific research, resource management, and governance. Alternatively, they might have evolved beyond traditional hierarchies altogether, perhaps adopting a more collaborative and decentralized approach. With their advanced technology, they could have developed sophisticated systems for collective decision-making and resource allocation, eliminating the need for rigid power structures. It's also conceivable that their social structures might be entirely alien to our understanding, shaped by factors we can't even imagine. Their long history and advanced evolution could have led to forms of social organization that are fundamentally different from anything we've seen on Earth, possibly integrating aspects of their technology or unique environmental conditions. Ancient civilizations held diverse and often imaginative views of the cosmos, vastly different from our modern understanding. Many believed the Earth was the center of the universe, with celestial bodies rotating around it. The ancient Greeks, for instance, envisioned crystalline spheres carrying planets and stars in perfect circular orbits. Some cultures saw the sky as a dome or firmament, a solid barrier separating the earthly realm from the heavens. Others, like ancient Egyptians, viewed the sky as the goddess Nut, arching over the earth. These beliefs often intertwined cosmology with mythology, attributing celestial phenomena to the actions of gods or supernatural beings. Unlike our current knowledge of an expanding universe billions of light-years across, ancient peoples generally conceived of a much smaller, more intimate cosmos. They lacked awareness of galaxies beyond our own, the true nature of stars as distant suns, or the existence of planets around other stars. Their universe was typically limited to what they could observe with the naked eye. Fundamentally, ancient understandings were based on direct observation and philosophical reasoning, without the benefit of modern scientific methods or advanced technology. This led to a rich tapestry of cosmic models, each reflecting the unique cultural and religious contexts of its origins, but ultimately limited in its ability to explain the true nature and scale of the universe as we know it today. An advanced civilization from the early universe would have had access to incredibly powerful energy sources. As the cosmos was much denser and hotter in its youth, these ancient beings could have harnessed the intense radiation and abundant matter surrounding them. Primordial black holes, formed in the extreme conditions following the Big Bang, could have served as potent energy generators. These cosmic powerhouses, far more common in the early universe, might have been tapped through advanced gravitational technologies, extracting vast amounts of energy from their intense gravitational fields and hawking radiation. The first generation of stars, known as Population 3 stars, would have been prime candidates for energy harvesting. These massive, short-lived stellar giants were composed almost entirely of hydrogen and helium, burning hotter and brighter than any stars we see today. An advanced civilization could have developed methods to capture and utilize the immense energy output of these cosmic behemoths. Cosmic strings, theoretical defects in the fabric of spacetime left over from the universe's birth, might have been another exotic power source. These ultra-dense strands of energy, if they existed, could have provided near-limitless power to those with the means to harness them. Such theoretical energy sources highlight the vast and often mind-bending possibilities available to advanced civilizations in the early cosmos. Alien communication methods could have undergone remarkable transformations over millions of years of evolution. Starting with simple chemical signals like those used by single-celled organisms on Earth, alien life might have developed increasingly complex forms of interaction. As their sensory organs evolved, they could have progressed to visual cues, sound waves, or even electromagnetic signals. Advanced alien civilizations might have moved beyond physical communication entirely, developing telepathic abilities or quantum entanglement-based systems that allow instant communication across vast distances. They could have engineered their own biology to incorporate technological components, creating a hybrid form of communication that merges organic and artificial intelligence. Some alien species might have evolved to perceive and manipulate dimensions beyond our understanding, using these additional planes of existence as communication channels. This could allow them to transmit vast amounts of information instantaneously, transcending the limitations of speed and distance that constrain our current communication methods. As their technology advanced, aliens might have developed ways to communicate through the fabric of spacetime itself, perhaps using gravitational waves or manipulating dark energy. These methods could potentially allow for communication across different points in time, fundamentally altering our understanding of cause and effect in the universe. Considering the immense age of such an ancient civilization, the survival of any artifacts would be truly remarkable. However, if we were to find remnants, they would likely be incredibly durable materials that could withstand the test of time. Structures or monuments made from extremely hard stone, similar to granite or basalt, might have endured. These could take the form of megalithic constructions akin to Earth's ancient wonders like Stonehenge or the Egyptian pyramids, but potentially on an even grander scale. Metals with exceptional resistance to corrosion, such as gold or platinum, might also have survived in some form. These could manifest as intricate jewelry, ceremonial objects, or even advanced technological components that have remained intact over the eons. It is conceivable that these artifacts might incorporate exotic materials unknown to our current science, possibly preserving their structure far better than anything we can create today. In terms of art, we might discover remnants of extremely durable ceramics or glass-like substances, potentially bearing intricate designs or symbols that could offer insights into the civilization's culture and aesthetics. Additionally, if this ancient society had achieved a level of technology far beyond our own, we might find artifacts made from synthetic materials designed specifically for longevity, perhaps even incorporating self-repairing nanotechnology. It is also possible that we might discover informational artifacts, such as records or data storage devices, made from materials capable of preserving information for billions of years. These could potentially contain vast libraries of knowledge, artistic creations, or historical records that could revolutionize our understanding of the universe and our place within it. Ancient human societies had a vastly different relationship with their environment compared to modern societies. These early cultures were intimately connected to the natural world around them, relying directly on their local ecosystems for survival. They developed deep knowledge of plants, animals, and natural cycles, often incorporating this understanding into their spiritual beliefs and daily practices. Unlike today's globalized world, ancient societies were limited by geography and climate. They adapted to their specific environments, developing unique tools, farming techniques, and cultural practices suited to their surroundings. This close connection fostered a sense of stewardship and respect for nature, as the health of the environment directly impacted their well-being. Resource use in ancient societies was generally more sustainable out of necessity. Without modern technology and global supply chains, they were forced to live within the limits of their local ecosystems. This led to practices such as crop rotation, controlled hunting, and seasonal migrations that helped maintain ecological balance. However, it is important to note that ancient societies were not always in perfect harmony with nature. Some civilizations did cause environmental damage through deforestation, overgrazing, or intensive agriculture. The difference lies in the scale and speed of impact, which was generally much smaller and slower than in our modern industrial world. Advanced civilizations in the universe could have made extraordinary scientific breakthroughs that surpass our current knowledge by leaps and bounds. They might have unlocked the secrets of dark matter and dark energy, understanding their true nature and harnessing their potential. These civilizations could have developed methods to manipulate gravity, allowing them to create artificial gravity fields or even warp space-time itself. Their understanding of quantum mechanics might be so advanced that they can exploit quantum effects on a macroscopic scale, leading to technologies like instantaneous communication across vast distances or the ability to exist in multiple states simultaneously. They may have mastered the art of creating and sustaining microscopic black holes, using them as powerful energy sources or as gateways to other parts of the universe. In the realm of biology, these advanced beings might have decoded the fundamental principles of life, allowing them to engineer entirely new forms of organisms or even create synthetic life from scratch. They could have developed ways to transfer consciousness between bodies or even into artificial substrates, effectively achieving a form of digital immortality. Perhaps most intriguingly, they might have made breakthroughs in understanding the nature of reality itself, discovering that our universe is part of a larger multiverse, or that consciousness plays a fundamental role in shaping the fabric of existence. Such advancements would revolutionize our understanding of science and the cosmos, opening up possibilities we can scarcely imagine with our current level of knowledge. Alien civilizations could have radically different perceptions of time and history compared to humans. Their lifespans might stretch for thousands of years, making our centuries seem like mere moments. This extended existence could lead to a vastly different understanding of historical events and long-term trends. Their planet might orbit its star at a different rate than Earth, resulting in longer or shorter years. This could affect how they measure and record the passage of time, potentially using entirely different units or systems. Some alien species might even experience time non-linearly, perceiving past, present, and future simultaneously. The geological and evolutionary history of their homeworld could also shape their view of time. A planet with less geological activity might have a more static environment, leading to a civilization that perceives change over much longer periods. Conversely, a highly volatile world might produce beings that are more attuned to rapid transformations. Their perception of history could be influenced by their methods of record-keeping. Advanced aliens might have perfect memory or technologies that allow them to experience historical events directly rather than relying on written accounts or oral traditions. This could result in a much more accurate and detailed understanding of their past than we have of our own. The Silurian hypothesis offers a fascinating perspective on the potential for advanced civilizations to exist on Earth long before humans. This thought experiment, proposed by scientists Adam Frank and Gavin Schmidt, explores the possibility that an industrial civilization could have thrived on our planet millions of years ago, leaving little to no trace of its existence. This hypothesis challenges us to consider the long-term survival and detectability of civilizations over geological timescales. It suggests that even a highly advanced society might not leave easily identifiable evidence after millions of years of erosion, plate tectonics, and other geological processes. This concept raises important questions about our ability to recognize the signs of past civilizations and the potential impermanence of our own technological achievements. The Silurian hypothesis also prompts us to reflect on the resilience of civilizations in the face of global challenges. If such an ancient civilization did exist, its disappearance might have been caused by factors similar to those we face today, such as climate change, resource depletion, or environmental degradation. This parallel encourages us to consider the long-term sustainability of our current practices and the potential consequences of our actions on a geological timescale. Furthermore, this hypothesis highlights the importance of developing more sophisticated methods for detecting signs of past civilizations, both on Earth and potentially on other planets. It challenges us to think creatively about the types of evidence that might persist over millions of years, pushing the boundaries of archaeology, geology, and related fields. By considering these possibilities, we may gain new insights into the nature of technological societies and their place in the vast expanse of cosmic time. 100 million years from now, our current civilization might appear as nothing more than a thin, enigmatic layer in the geological record. Time and natural processes would have eroded and transformed most of our structures and artifacts beyond recognition. Researchers of the distant future would likely struggle to piece together evidence of our existence, much as we now study ancient extinct species and long-lost cultures. Our most enduring legacy might be the changes we've made to Earth's atmosphere and ecosystems. Future scientists could detect unusual concentrations of carbon dioxide and other greenhouse gases in rock layers corresponding to our era. They might also find traces of synthetic materials, such as plastics and certain metals, scattered throughout sedimentary deposits. In urban areas, the remains of our tallest and most robust buildings might persist as unusual geological formations. Underground structures like subways and bunkers could leave perplexing voids or patterns in rock strata. However, most of our cities and infrastructure would have long since crumbled and been reabsorbed into the earth. Perhaps the most striking evidence of our civilization would be the sudden appearance and disappearance of many species in the fossil record, marking the ongoing mass extinction event we've triggered. Future researchers might marvel at this abrupt shift in Earth's biodiversity, puzzling over what force could have caused such rapid and widespread changes across the planet. Preserving evidence of our existence for millions of years presents a monumental challenge. Our most durable materials, like certain plastics and metals, might last thousands of years, but not millions. However, we can take inspiration from nature and ancient civilizations to create long-lasting records. One approach is to carve or etch information into extremely hard, stable rock formations. Granite or basalt could serve as natural time capsules, potentially lasting millions of years if protected from erosion. We could create vast underground chambers in geologically stable areas, filled with information about our civilization encoded in various formats. Another strategy involves sending artifacts into space. Objects placed in stable orbits around the Sun or on the surface of the Moon could remain intact for extraordinary periods. We could design specially crafted satellites or lunar monuments containing comprehensive records of human knowledge and achievement. Developing new, ultra-durable materials and storage methods is crucial. Scientists are exploring techniques like storing data in synthetic DNA or etching information onto sapphire disks with platinum. These cutting-edge approaches aim to create archives that could theoretically survive for millions of years, ensuring that some trace of our existence endures far into the future. The Silurian hypothesis challenges our understanding of Earth's history and our place in it. This thought-provoking concept suggests that an advanced civilization might have existed on our planet millions of years ago, leaving little to no trace of their presence. While named after a fictional race from Doctor Who, the hypothesis raises serious questions about our ability to detect past technological societies. This idea forces us to reconsider how we view the longevity and impact of our own civilization. If an advanced society could rise and fall without leaving clear evidence, it implies that our current technological achievements might also vanish given enough time. The Earth's geological processes, such as plate tectonics and erosion, could erase most signs of our existence over millions of years. The Silurian hypothesis also prompts us to think about the potential cyclical nature of advanced civilizations on Earth. It suggests that our species might not be the first to achieve technological sophistication, raising questions about the uniqueness of human intelligence and our role in the planet's history. This perspective encourages humility and a broader view of our place in Earth's timeline. Furthermore, this hypothesis influences our approach to searching for extraterrestrial intelligence. If we struggle to find evidence of past advanced civilizations on our own planet, it highlights the challenges we might face in detecting alien civilizations across the vast distances of space. This realization emphasizes the need for more diverse and sensitive methods in our search for intelligent life beyond Earth. As the current stewards of Earth's knowledge and culture, we bear a profound responsibility to future civilizations. Our duty extends beyond mere preservation. We must ensure that the vast wealth of human understanding remains accessible and comprehensible to those who will inherit our world. One of our primary obligations is to safeguard scientific knowledge. This includes not only our current understanding of the universe, from the subatomic realm to the cosmic scale, but also the methods and principles that have led to these discoveries. We must strive to maintain detailed records of our scientific advancements, experimental procedures, and theoretical frameworks, allowing future generations to build upon our work and push the boundaries of knowledge even further. Equally important is the preservation of our cultural heritage. Languages, art, literature, music, and historical records all form the tapestry of human experience. By protecting these cultural treasures, we provide future civilizations with invaluable insights into the human condition and the evolution of our societies. This cultural continuity can serve as a bridge across time, connecting distant generations and fostering a sense of shared humanity. We also have a responsibility to document the challenges we face and the solutions we develop. Climate change, resource management, global health crises, and technological ethics are just a few of the complex issues that will likely persist or evolve in the future. By thoroughly recording our approaches, successes, and failures in addressing these challenges, we can offer crucial guidance to future problem solvers, potentially helping them avoid pitfalls and build upon our progress. The cycle of civilizations rising and falling could extend far into the future, driven by factors both familiar and unprecedented. As humanity expands beyond Earth, we might see the emergence of interplanetary or even interstellar civilizations, each facing unique challenges that could lead to their eventual decline. Resource scarcity, a common factor in the fall of past civilizations, could manifest on a cosmic scale. Advanced societies might deplete the resources of entire planets or star systems, forcing migrations to new cosmic neighborhoods. This could lead to conflicts between expanding civilizations, potentially causing widespread collapse. Technological advancements could play a dual role in this cycle. While they might initially propel civilizations to great heights, they could also contribute to their downfall. For instance, artificial intelligence surpassing human control or the development of weapons capable of destroying entire worlds could pose existential threats to even the most advanced societies. Environmental factors would likely continue to influence the rise and fall of civilizations, but on a grander scale. Climate changes on colonized planets, stellar events like supernovae, or even shifts in the cosmic environment could force adaptations or lead to the decline of once thriving cultures. The resilience and adaptability of future civilizations in the face of these cosmic challenges would determine their longevity in the vast theater of space and time. To preserve information for the distant future, we need to develop robust and long-lasting storage methods. One promising approach is using synthetic DNA as a data storage medium. DNA can potentially store vast amounts of information in a tiny space and remain stable for thousands of years under proper conditions. Scientists are working on techniques to encode digital data into DNA sequences and later retrieve that information accurately. Another important strategy is to create time capsules designed to endure for millennia. These could be constructed from highly durable materials like tungsten or sapphire, resistant to environmental degradation. Such capsules could contain a variety of information formats, from engraved metal plates to advanced digital storage devices, ensuring redundancy and increasing the chances of future recovery. We should also consider off-world storage solutions. Establishing data repositories on the Moon or other celestial bodies could protect information from Earth-based catastrophes. These lunar libraries could be shielded from radiation and extreme temperature fluctuations, preserving data for future generations or potential extraterrestrial discoverers. Developing universal communication methods is equally crucial. We need to create systems for encoding information that could be understood by future civilizations, even if they don't share our language or technology. This might involve using mathematical or pictorial languages that convey fundamental scientific and cultural concepts, ensuring our knowledge remains accessible across vast stretches of time. The potential existence of past advanced civilizations in our universe significantly impacts our approach to long-term space exploration. This intriguing concept, known as the Silurian hypothesis, suggests that Earth or other planets might have hosted technologically advanced societies millions or even billions of years ago, leaving little to no detectable evidence of their existence. This possibility compels us to broaden our search parameters and refine our detection methods when exploring other worlds. We must look beyond obvious signs of current life and consider subtle geological or chemical signatures that could indicate past technological activity. For instance, we might search for unusual concentrations of synthetic materials or unexpected isotope ratios in planetary crusts. The idea of ancient advanced civilizations also influences our understanding of the challenges facing long-term survival in space. If such societies existed and disappeared, we must consider what factors led to their downfall and how we can avoid similar fates. This could involve developing more robust and self-sustaining space habitats, improving our ability to detect and mitigate cosmic threats, and creating technologies capable of withstanding extreme timescales. Furthermore, this concept underscores the importance of developing technologies for interstellar travel and communication. If advanced civilizations have risen and fallen multiple times across the cosmos, the window for contact between contemporaneous societies might be exceedingly narrow. This realization adds urgency to our efforts to reach beyond our solar system and establish a lasting human presence in space. The potential downfall of an advanced ancient civilization offers valuable insights into the fragility of progress and the cyclical nature of human development. By examining such a scenario, we can gain a deeper understanding of the complex factors that contribute to societal collapse and the long-term consequences of technological and cultural loss. One key lesson is the importance of sustainable resource management. An advanced civilization that overexploits its environment or fails to adapt to changing climate conditions may find itself unable to support its population or maintain its technological infrastructure. This serves as a stark reminder of our own need to balance progress with ecological stewardship. The loss of knowledge and technology that would accompany such a collapse highlights the critical role of information preservation and transmission. Without robust systems to maintain and pass on scientific and cultural knowledge, even the most advanced society could regress, leaving future generations to rediscover lost innovations. This underscores the value of diverse and resilient methods of storing and sharing information across time and space. Furthermore, the hypothetical downfall of an advanced civilization emphasizes the need for societal resilience and adaptability. Factors such as social inequality, political instability, or over-reliance on complex systems could contribute to a civilization's vulnerability. By recognizing these potential weaknesses, we can work to build more robust and flexible societies capable of weathering various challenges and maintaining long-term stability and progress. The discovery of a past advanced civilization would profoundly alter our perspective on existential risks and potentially reshape our strategies for long-term survival. Such a finding would provide tangible evidence that intelligent life can arise and develop advanced technologies, yet still face extinction or collapse. This revelation would likely intensify our focus on identifying and mitigating existential threats. We would scrutinize the fate of this lost civilization, searching for clues about what led to their downfall. Was it a natural disaster, like an asteroid impact or supervolcano eruption? Did they succumb to the consequences of climate change or resource depletion? Or perhaps they fell victim to the dangers of their own technological advancements, such as artificial intelligence or weapons of mass destruction. Understanding the specific challenges that overwhelmed this ancient society could help us prioritize our own existential risk mitigation efforts. For instance, if we found evidence of a catastrophic technological failure, we might place greater emphasis on developing robust safety protocols for emerging technologies. Alternatively, if their demise was linked to environmental factors, it could drive more urgent action on climate change and ecological preservation. Moreover, the very existence of such a civilization would underscore the importance of long-term thinking and planning. It would serve as a stark reminder that even highly advanced societies can be vulnerable, prompting us to consider multi-generational strategies for ensuring human survival and progress. This could lead to increased investment in space exploration and colonization efforts, viewing them as essential backup plans for humanity rather than mere scientific endeavors. Science fiction has played a significant role in shaping scientific thinking about ancient advanced civilizations, sparking curiosity and inspiring researchers to explore new possibilities. The concept of highly developed societies predating our own has captured the imagination of both writers and scientists, leading to a fascinating interplay between speculative fiction and serious academic inquiry. Many science fiction stories have portrayed lost civilizations with advanced technology, often suggesting they might have had contact with extraterrestrial beings. These narratives have encouraged scientists to consider unconventional ideas and examine historical evidence from new perspectives. For instance, the popular notion of ancient astronauts visiting Earth has prompted archaeologists to re-evaluate mysterious artifacts and structures, seeking alternative explanations for their creation. Furthermore, science fiction has influenced the development of new technologies and research methods used in the study of ancient civilizations. Ideas first proposed in fictional works, such as advanced imaging techniques or the use of artificial intelligence in archaeological analysis, have sometimes preceded and inspired real-world innovations. This has led to breakthroughs in our understanding of ancient cultures and their capabilities. While maintaining scientific rigor, researchers have become more open to considering the possibility of sophisticated ancient societies possessing knowledge and skills beyond what was previously thought possible. This shift in perspective has resulted in a more nuanced and complex view of human history, challenging long-held assumptions about the linear progression of technological advancement. The Silurian hypothesis, which proposes the possibility of an advanced civilization existing on Earth millions of years before humans, has inspired various science fiction works. One notable example is Arthur C. Clarke's The City and the Stars, which explores the concept of ancient, highly advanced civilizations. In this novel, Clarke imagines a city that has existed for billions of years, preserving the last remnants of humanity. Another relevant work is the Dragon Riders of Pern series by Anne McCaffrey. While not directly addressing the Silurian hypothesis, these books feature a human colony on a distant planet that regresses technologically and rediscovers its advanced origins after thousands of years. This concept mirrors the idea of lost civilizations and forgotten knowledge central to the Silurian hypothesis. The Engines of God series by Jack McDevitt also touches on similar themes. These books involve archaeologists discovering remnants of ancient alien civilizations, echoing the idea of searching for evidence of past advanced societies on Earth. The series explores the challenges of interpreting artifacts and structures left behind by long-gone cultures, much like the difficulties posed by the Silurian hypothesis. Stephen Baxter's Evolution takes a unique approach, tracing the history of life on Earth across millions of years. While not focusing on a pre-human civilization, it explores the potential for intelligence and technology to arise in species other than humans, aligning with the broader implications of the Silurian hypothesis. Science fiction narratives serve as powerful tools for imagining the possibilities of ancient civilizations, bridging the gap between our limited archaeological evidence and the vast unknowns of the past. These stories allow us to explore potential technological advancements, social structures, and cultural practices that might have existed in long-lost societies. By crafting detailed worlds and advanced civilizations, science fiction authors often draw inspiration from real historical mysteries and archaeological findings. This process can spark new ideas and hypotheses about how ancient peoples might have lived, worked, and interacted with their environment. For instance, stories about advanced ancient technologies can prompt researchers to look for evidence of sophisticated engineering in archaeological sites. Moreover, science fiction narratives help us challenge our assumptions about the linear nature of progress. They encourage us to consider that ancient civilizations might have developed technologies or knowledge that we have yet to rediscover. This perspective can lead to more open-minded approaches in archaeological and historical research, potentially uncovering overlooked evidence or reinterpreting existing data. These imaginative explorations also serve to captivate public interest in ancient history and archaeology. By presenting engaging visions of the past, science fiction can inspire a new generation of researchers and enthusiasts to delve deeper into the mysteries of our ancestors, potentially leading to real-world discoveries and advancements in our understanding of human history. Speculative fiction serves as a powerful catalyst for scientific inquiry, sparking the imagination of researchers and inspiring new avenues of exploration. By envisioning potential futures and alternative realities, authors of science fiction often anticipate technological advancements and scientific discoveries years or even decades before they become reality. Many concepts that were once purely fictional have now become subjects of serious scientific study. For instance, the idea of faster-than-light travel, a staple of science fiction, has led scientists to investigate the theoretical possibilities of warp drives and wormholes. Similarly, the notion of artificial intelligence, long explored in literature, has become a rapidly advancing field of research and development. Speculative fiction also encourages scientists to think beyond current paradigms and consider unconventional solutions to complex problems. It provides a framework for exploring the potential consequences of scientific advancements, both positive and negative, prompting researchers to consider ethical implications and societal impacts of their work. Moreover, science fiction often serves as a bridge between scientific concepts and public understanding, making complex ideas more accessible and generating public interest in scientific pursuits. This increased engagement can lead to greater support for research funding and inspire a new generation of scientists to push the boundaries of human knowledge. The Silurian hypothesis, proposed by scientists Adam Frank and Gavin Schmidt, explores the possibility that an advanced civilization might have existed on Earth millions of years ago, leaving little to no trace for us to find today. This intriguing concept has been significantly influenced by media portrayals of ancient advanced civilizations, shaping public perception in several ways. Popular culture, including movies, television shows, and books, has long been fascinated with the idea of lost civilizations and hidden histories. These fictional narratives often depict highly advanced societies existing in the distant past, complete with advanced technology and knowledge that rivals or surpasses our own. Such portrayals have primed the public to be more receptive to ideas like the Silurian hypothesis, creating a sense of plausibility and excitement around the concept. However, this media influence has also led to some misconceptions. Many fictional depictions of ancient advanced civilizations focus on humanoid species, whereas the Silurian hypothesis considers the possibility of non-human intelligent life forms. This has sometimes resulted in a public misunderstanding of the hypothesis, with people imagining ancient humans with modern technology rather than potentially unrecognizable forms of intelligent life. Media portrayals have also contributed to both skepticism and enthusiasm regarding the Silurian hypothesis. While some view it as an exciting possibility worth exploring, others dismiss it as science fiction come to life. This divide in public opinion reflects the complex relationship between scientific hypotheses and their representation in popular culture, highlighting the need for clear communication of scientific ideas to the general public. Fictional accounts of discovering ancient advanced civilizations offer intriguing insights into our understanding of history, technology, and human nature. These stories often challenge our assumptions about the linear progression of human development and technological advancement. They encourage us to consider the possibility that our ancestors may have possessed knowledge or capabilities we have yet to fully comprehend or rediscover. These narratives frequently explore the impact of such discoveries on contemporary society, prompting us to reflect on our own technological progress and its potential consequences. They raise questions about the cyclical nature of civilizations, suggesting that advanced societies might rise, fall, and be forgotten over vast stretches of time. This concept encourages a broader perspective on our place in history and the potential impermanence of our own achievements. Moreover, these fictional accounts often serve as a mirror to our own society, highlighting our fears, aspirations, and ethical dilemmas. They may explore themes of power, knowledge, and responsibility, asking how we might handle the discovery of advanced ancient technologies or the realization that we are not the first to achieve certain scientific milestones. This can lead to valuable discussions about the use and misuse of technology, the importance of preserving knowledge, and the potential dangers of unchecked progress. Ultimately, while these stories are fictional, they stimulate our imagination and critical thinking. They encourage us to question our assumptions, consider alternative historical narratives, and reflect on the nature of progress and civilization. In doing so, they can inspire real-world archaeological and historical research, driving us to look at our past with fresh eyes and an open mind. Science fiction authors face a unique challenge when depicting ancient civilizations, as they must weave together scientific plausibility and engaging storytelling. To achieve this balance, many authors start by grounding their work in established scientific theories and archaeological evidence. They might draw inspiration from real ancient cultures, extrapolating from known historical facts to create believable yet fantastical societies. One common approach is to incorporate cutting-edge scientific concepts into the fabric of these ancient civilizations. For instance, an author might imagine an advanced alien race that harnessed quantum mechanics or manipulated dark energy, long before humans even understood basic physics. This technique allows for both scientific intrigue and narrative flexibility, as the author can explore the potential consequences of such advanced knowledge on societal development. Authors often employ the concept of parallel evolution or convergent technological development to explain similarities between ancient alien civilizations and human cultures. This approach helps readers relate to the story while maintaining a sense of otherworldliness. Additionally, many writers use the idea of lost or hidden knowledge to bridge the gap between ancient advanced civilizations and contemporary science, suggesting that some of our modern discoveries might be rediscoveries of long-forgotten wisdom. Ultimately, successful science fiction authors strike a delicate balance between scientific accuracy and creative liberty. They use established scientific principles as a foundation while allowing their imagination to fill in the gaps, creating worlds that are both wondrous and plausible. This blend of fact and fiction not only entertains readers, but also encourages them to ponder the possibilities of our universe and the potential for advanced civilizations beyond our current understanding. The ancient astronaut theory, popularized in science fiction, has had a complex and often contentious relationship with serious scientific inquiry. While professional scientists overwhelmingly reject the idea that extraterrestrial beings influenced early human civilizations, the theory's presence in popular culture has indirectly spurred interest in archaeology, anthropology, and space exploration. Some researchers have been motivated to conduct more thorough investigations of ancient sites and artifacts to provide evidence-based explanations for mysterious structures or technologies. This has led to improved understanding of ancient engineering techniques and cultural practices, effectively debunking many claims made by ancient astronaut theorists. The theory has also prompted discussions about the nature of evidence in scientific research. Scientists have had to clearly articulate the standards of proof required to support extraordinary claims, emphasizing the importance of peer review and reproducible results. This has helped strengthen the scientific method and improve public understanding of how scientific knowledge is established. However, the persistence of ancient astronaut ideas in popular media has sometimes created challenges for scientists attempting to communicate factual information about human history and the search for extraterrestrial life. Researchers must often address misconceptions stemming from these fictional narratives, which can divert time and resources from more productive avenues of inquiry. Science fiction scenarios about past civilizations serve as a fascinating lens through which we can explore potential future discoveries. These imaginative tales often spark curiosity and encourage scientists to consider unconventional possibilities in their research. One way these scenarios influence our thinking is by prompting us to look for evidence of advanced technologies in ancient contexts. For example, stories of lost civilizations with advanced capabilities have inspired archaeologists to search for anomalies that might indicate sophisticated engineering or scientific knowledge in prehistoric sites. This approach has led to some intriguing discoveries, such as the precise astronomical alignments in ancient structures. Furthermore, science fiction about past civilizations challenges us to reconsider our assumptions about technological progress. It raises questions about whether advanced societies might have existed and collapsed in cycles throughout history, leaving behind only subtle traces. This perspective encourages researchers to remain open-minded when interpreting archaeological and geological evidence, potentially leading to new insights about our planet's past. These imaginative scenarios also inform our thinking about the potential longevity and resilience of our own civilization. By contemplating fictional advanced societies that have vanished, we are compelled to consider the challenges we might face in preserving our knowledge and achievements for future generations. This reflection can guide our approach to long-term planning and the development of technologies designed to withstand the test of time. Science fiction creators play a crucial role in shaping public understanding of scientific concepts, including theories like the Silurian hypothesis. This hypothesis proposes that an advanced civilization might have existed on Earth millions of years ago, leaving little to no trace of their presence. While it's an intriguing concept, it's important for creators to strike a balance between entertainment and scientific accuracy. Responsible science fiction should present such theories in a way that clearly distinguishes between established scientific facts and speculative ideas. Creators have a duty to research and consult with experts to ensure their portrayals are grounded in current scientific understanding. This approach helps prevent the spread of misinformation and fosters critical thinking among audiences. However, science fiction also serves as a platform for exploring possibilities and inspiring scientific inquiry. By presenting theories like the Silurian hypothesis in a thoughtful manner, creators can encourage viewers to question our assumptions about Earth's history and the nature of civilization. They can spark curiosity about paleontology, geology, and the challenges of detecting ancient technological societies. Ultimately, the responsibility of science fiction creators lies in presenting these ideas as what they are: thought experiments and speculative scenarios. By doing so, they can entertain and educate simultaneously, potentially inspiring future scientists to explore new avenues of research. Researchers investigating claims of ancient advanced civilizations must adhere to strict ethical standards to ensure their work is credible and respectful. First and foremost, they should approach all claims with an open mind while maintaining scientific rigor. This means carefully examining evidence without preconceived notions, but also subjecting findings to peer review and scrutiny. Respect for cultural heritage is paramount. Researchers must work closely with local communities and indigenous peoples, obtaining proper permissions and involving them in the research process. This collaboration helps prevent the exploitation of sacred sites or artifacts and ensures that local knowledge and perspectives are valued. Transparency is crucial in this field. Researchers should clearly document their methods, share data openly, and be willing to admit uncertainties or limitations in their findings. They must also be cautious about sensationalizing results, as claims about ancient advanced civilizations can be easily misinterpreted or misused. Lastly, researchers have an ethical obligation to consider the broader implications of their work. They should be prepared to address how their findings might impact current understanding of human history and development, and be ready to engage in constructive dialogue with both the scientific community and the public. Scientists often navigate a complex landscape when balancing their pursuit of knowledge with respect for cultural beliefs and practices. This delicate equilibrium requires sensitivity, open communication, and a willingness to engage with diverse perspectives. In many cases, scientists work to find common ground between scientific inquiry and cultural traditions. They may collaborate with local communities, incorporating traditional knowledge into their research methods. This approach not only respects cultural practices, but can also lead to valuable insights that might otherwise be overlooked. However, conflicts can arise when scientific findings challenge deeply held beliefs. In these situations, scientists strive to present their discoveries clearly and objectively, while acknowledging the importance of cultural heritage. They may engage in dialogue with community leaders, explaining the scientific process and its implications, while also listening to and learning from alternative viewpoints. Ultimately, the goal is to advance scientific understanding while fostering mutual respect and understanding. This process often involves patience, diplomacy, and a recognition that both science and culture play crucial roles in shaping our understanding of the world around us. Misinterpreting or misrepresenting evidence related to ancient civilizations can have far-reaching consequences that ripple through our understanding of history, culture, and human development. When archaeologists or historians draw incorrect conclusions from artifacts or sites, it can lead to a distorted view of past societies and their achievements. One significant consequence is the perpetuation of false narratives about ancient peoples. These inaccuracies can reinforce stereotypes or misconceptions, potentially diminishing the true accomplishments of certain cultures while overstating those of others. This skewed perspective can influence modern cultural identities and even international relations, as nations and ethnic groups often derive pride and legitimacy from their historical roots. Moreover, misinterpretation of evidence can misdirect future research efforts and funding. Scholars might spend years pursuing theories based on flawed initial assessments, diverting resources from more productive avenues of study. This can slow down overall progress in our understanding of human history and delay important discoveries that could shed light on crucial aspects of our past. Perhaps most critically, misrepresenting ancient evidence can undermine public trust in archaeology and historical research. When high-profile claims are later debunked or significantly revised, it can lead to skepticism about scientific methods and findings in general. This erosion of trust may make it more challenging for legitimate researchers to gain support for their work and communicate important discoveries to the public, ultimately hindering our collective ability to learn from and appreciate the rich tapestry of human civilization. When researchers encounter evidence that could revolutionize our understanding of the universe, they must approach it with a blend of excitement and rigorous skepticism. The scientific method demands careful verification and peer review before any groundbreaking claims can be accepted. The first step is thorough documentation and repeated testing to ensure the evidence is reproducible and not the result of experimental error or equipment malfunction. Researchers should then seek input from colleagues, inviting them to scrutinize the data and methodology. This collaborative approach helps identify potential flaws or alternative explanations that the original team might have overlooked. If the evidence continues to hold up under scrutiny, the next phase involves preparing a comprehensive report for publication in a respected scientific journal. This process subjects the findings to peer review, where experts in the field critically examine the research. Only after passing this rigorous evaluation should the discovery be announced to the wider scientific community and the public. Throughout this process, Researchers must remain open to the possibility that their initial interpretations could be wrong or incomplete. Science progresses through constant questioning and refinement of ideas, even when dealing with potentially revolutionary discoveries. By adhering to these principles, scientists ensure that paradigm-shifting evidence receives the careful consideration it deserves while maintaining the integrity of scientific inquiry. Archaeologists face numerous ethical challenges when excavating or studying potential ancient habitation sites. One of the primary concerns is the preservation of cultural heritage. Excavations inevitably disturb or destroy parts of the site, so researchers must carefully weigh the potential knowledge gained against the loss of irreplaceable artifacts and structures. Another crucial consideration is the involvement and consent of local communities, especially indigenous peoples who may have ancestral ties to the site. Respecting their cultural beliefs, traditions, and rights to the land is paramount. This often involves extensive consultation and collaboration with community leaders and elders to ensure that excavations are conducted in a culturally sensitive manner. The ownership and disposition of artifacts discovered during excavations also raise ethical questions. Many countries have laws governing the export of cultural artifacts, and there is ongoing debate about whether items should remain in their country of origin or be housed in international museums. Archaeologists must navigate these complex legal and ethical landscapes while ensuring proper conservation and study of the artifacts. Finally, there are concerns about the potential exploitation of archaeological sites for tourism or commercial purposes. While public engagement can be beneficial for education and funding, it must be balanced against the need to protect fragile sites from damage and looting. Ethical archaeologists strive to find a middle ground that allows for scientific study and public appreciation while safeguarding these invaluable windows into our shared human past. Scientists have developed a robust system of checks and balances to address the potential exploitation of discoveries for personal gain or fame. This system includes peer review, replication studies, and ethical guidelines that form the foundation of scientific integrity. Peer review serves as the first line of defense against exploitation. Before research is published, it undergoes scrutiny by experts in the field who evaluate the methodology, results, and conclusions. This process helps identify flaws, biases, or potential conflicts of interest that might compromise the validity of the work. Replication studies play a crucial role in verifying scientific claims. Other researchers attempt to reproduce the results of important discoveries, ensuring that findings are not the product of manipulation or chance. This practice also helps uncover any unintentional errors or biases that may have influenced the original research. Scientific institutions and funding bodies have established strict ethical guidelines and codes of conduct. These rules outline proper research practices, data management, and publication standards. Scientists who violate these guidelines risk damaging their reputation, losing funding, or even facing legal consequences. This system of accountability helps deter those who might be tempted to exploit their work for personal gain. Researchers bear a crucial responsibility in sharing their discoveries with the wider world. As stewards of knowledge, they must bridge the gap between complex scientific concepts and public understanding. This involves translating technical jargon into accessible language without sacrificing accuracy or oversimplifying the subject matter. One key duty is ensuring transparency about the research process, including methods, limitations, and potential biases. By openly discussing these aspects, scientists help foster trust and critical thinking among the public. They should also contextualize their findings within the broader scientific landscape, explaining how new discoveries build upon or challenge existing knowledge. Researchers must strive to convey the implications and potential applications of their work. This helps the public grasp the relevance of scientific advancements to their daily lives and society at large. However, scientists should be cautious not to overstate or sensationalize their results, maintaining a balance between generating interest and upholding scientific integrity. Engaging with the media and participating in public outreach programs are vital components of a researcher's responsibilities. By actively seeking opportunities to communicate their work through various channels, scientists can combat misinformation, inspire future generations of researchers, and contribute to a more scientifically literate society. This ongoing dialogue between researchers and the public is essential for informed decision-making and the advancement of human knowledge. The scientific community thrives on healthy debate and scrutiny of evidence. When disagreements arise in interpreting data, scientists employ a rigorous process of peer review and open discussion. This involves presenting findings at conferences, publishing detailed methodologies, and subjecting results to independent verification. Researchers are encouraged to challenge existing theories and propose alternative explanations, provided they can support their claims with robust evidence. This process of questioning and testing is fundamental to scientific progress. When conflicts occur, scientists often design new experiments or gather additional data to resolve discrepancies. Collaboration plays a crucial role in addressing disagreements. Scientists from different institutions may work together to analyze data from multiple perspectives, combining expertise to reach more comprehensive conclusions. In some cases, conflicting interpretations lead to the development of new research techniques or the discovery of previously unknown phenomena. Ultimately, the scientific community values consensus built on evidence rather than individual opinions. While debates may persist for years or even decades, the accumulation of data and repeated testing generally lead to a convergence of understanding. This approach ensures that scientific knowledge evolves and improves over time, even in the face of initial disagreements. The use of advanced technology to search for ancient civilizations raises several complex ethical considerations. One primary concern is the potential disruption or destruction of archaeological sites. Powerful scanning and excavation tools could inadvertently damage delicate artifacts or structures, erasing valuable historical information. This risk becomes even more pronounced when dealing with cultures that have living descendants who may view these sites as sacred or culturally significant. Another ethical issue revolves around the ownership and control of discovered artifacts or knowledge. There are ongoing debates about whether items should be returned to their countries of origin or kept in museums worldwide. Advanced technology could exacerbate these tensions by enabling more efficient and widespread discoveries, potentially leading to conflicts over who has the right to study, possess, or profit from these findings. Privacy and consent also come into play, especially when technology allows us to peer into ancient tombs or burial sites without physical intrusion. While this approach minimizes physical damage, it raises questions about respecting the wishes of the deceased and their descendants. Furthermore, the use of genetic analysis on ancient remains can reveal information about living populations, raising concerns about genetic privacy and the potential for misuse of this data. Lastly, there is the risk of cultural bias in how we interpret and present findings. Advanced technology might allow us to uncover vast amounts of information, but our interpretation of this data could be influenced by our own cultural perspectives. This could lead to misrepresentations of ancient civilizations or the reinforcement of harmful stereotypes. Balancing scientific curiosity with ethical responsibility and cultural sensitivity remains a crucial challenge in this field. Researchers in the scientific community often find themselves walking a delicate line when it comes to the political implications of their work. The pursuit of knowledge can sometimes lead to discoveries that challenge existing power structures or societal norms, requiring scientists to carefully consider how they present and discuss their findings. One key approach is maintaining strict adherence to the scientific method and focusing on presenting data and conclusions as objectively as possible. By emphasizing the rigor of their methodology and the reliability of their results, researchers can help separate their work from potential political interpretations. This approach allows the facts to speak for themselves, leaving policymakers and the public to draw their own conclusions. However, scientists also recognize their responsibility to communicate the broader implications of their work. Many researchers engage in public outreach, participating in interviews, writing articles, or giving lectures to help contextualize their findings for a general audience. In these efforts, They strive to balance scientific accuracy with clear, accessible explanations that highlight the relevance of their work without veering into political advocacy. Collaboration and peer review play crucial roles in navigating potential political landmines. By working with colleagues from diverse backgrounds and subjecting their work to rigorous peer review, researchers can identify and address potential biases or controversial aspects of their findings before publication. This process helps ensure that the final results are as robust and defensible as possible, regardless of their political implications. The Silurian hypothesis challenges our perspective on Earth's history and climate change. This thought-provoking idea suggests that an advanced civilization might have existed on our planet millions of years ago, potentially altering the climate in ways similar to our current impact. While there is no evidence supporting this hypothesis, it serves as a valuable tool for considering the long-term effects of human activity on the planet. Examining the geological record for signs of past civilizations highlights the limitations of our ability to detect long-term climate change impacts. The hypothesis proposes that after millions of years, most traces of an advanced society would be erased, leaving only subtle chemical signatures in rock layers. This concept forces us to consider how our own civilization's effects might be perceived in the distant future. The Silurian hypothesis also emphasizes the importance of understanding natural climate variability over extremely long timescales. By contemplating the possibility of past advanced civilizations, scientists are encouraged to develop more sophisticated methods for distinguishing between natural climate fluctuations and anthropogenic changes. This approach enhances our overall comprehension of Earth's complex climate system. Ultimately, while the Silurian hypothesis remains speculative, it serves as a valuable thought experiment. It pushes us to think critically about the long-term consequences of our actions on the planet and the challenges of detecting significant climate alterations over geological timescales. This perspective is crucial as we grapple with our own impact on Earth's climate and strive to understand and mitigate long-term environmental changes. Exploring the concept of past advanced civilizations offers intriguing insights into sustainability. By examining hypothetical scenarios of civilizations that may have risen and fallen on Earth or other planets, we can gain valuable perspectives on long-term resource management and environmental stewardship. One key lesson emerges from considering the potential downfall of advanced societies: the critical importance of balancing technological progress with ecological preservation. If past civilizations existed and collapsed, their demise might have been linked to resource depletion or environmental degradation. This underscores the need for our own civilization to develop sustainable practices that can endure for millennia, not just decades or centuries. The possibility of undetected ancient advanced societies also highlights the impermanence of technological achievements. Even if a civilization reaches great heights, its legacy can be erased by time if it fails to achieve true sustainability. This realization emphasizes the importance of creating lasting, regenerative systems rather than relying on temporary solutions or short-term gains. Furthermore, contemplating past advanced civilizations reminds us of the vast timescales involved in planetary and cosmic processes. It encourages us to think beyond immediate concerns and consider the long-term consequences of our actions on Earth and potentially beyond. This expanded perspective can inspire more responsible decision-making and innovative approaches to ensuring the longevity of our own civilization. The exploration of hypothetical ancient civilizations offers valuable insights that can shape our approach to modern environmental challenges. By examining potential scenarios of advanced societies that may have existed in Earth's distant past, we can gain fresh perspectives on sustainable practices and long-term planetary stewardship. These theoretical civilizations could have developed innovative solutions to environmental problems that we currently face. For instance, they might have mastered efficient resource management techniques or discovered renewable energy sources that we have yet to consider. Studying their hypothetical methods could inspire new directions in our own research and development of green technologies. Furthermore, Investigating the potential downfall of these ancient societies due to environmental factors could serve as a cautionary tale for our own civilization. If these advanced cultures ultimately collapsed due to resource depletion, climate change, or ecological imbalance, we might recognize similar patterns in our current trajectory and take corrective action before it is too late. By combining the study of these hypothetical ancient civilizations with our understanding of Earth's geological and climatological history, we can develop more comprehensive models for predicting long-term environmental changes. This approach encourages us to think on larger timescales and consider the far-reaching consequences of our actions, ultimately leading to more sustainable decision-making in the present. The Silurian hypothesis, proposed by scientists Gavin Schmidt and Adam Frank, challenges us to consider the possibility of advanced civilizations existing on Earth long before humans. This thought experiment offers intriguing insights into the long-term effects of technological development on a planet. One key insight is the potential impermanence of technological artifacts over geological timescales. Even our most durable structures and materials would likely be erased by natural processes within a few million years. This suggests that if an advanced civilization existed in Earth's distant past, direct evidence of their technology might be difficult or impossible to find today. The hypothesis also highlights the importance of examining subtle, long-lasting changes to the planet's systems. An advanced civilization might leave detectable traces in the geological record, such as changes in carbon isotope ratios, unusual concentrations of certain elements, or shifts in sedimentation patterns. These indirect markers could persist far longer than physical remains of technology. Furthermore, the Silurian hypothesis encourages us to consider the potential environmental impacts of advanced technology over extremely long periods. It prompts questions about how our current civilization might be altering Earth's systems in ways that could be detectable millions of years from now, and what those changes might mean for the planet's future inhabitants. The concept of past civilizations on Earth profoundly impacts our understanding of our planet's carrying capacity. When we consider the rise and fall of ancient societies, we gain valuable insights into the long-term sustainability of human populations and resource usage. Archaeological evidence reveals that numerous advanced civilizations have flourished and then collapsed throughout Earth's history. The Mayan civilization of Central America, the Indus Valley culture of ancient India, and the Easter Island society all experienced significant population declines or complete collapses. These historical examples demonstrate that even sophisticated cultures can exceed their local environmental limits. Studying these past civilizations allows us to identify critical factors that contribute to societal collapse, such as resource depletion, climate change, and unsustainable agricultural practices. By analyzing their mistakes and successes, we can better estimate Earth's current carrying capacity and develop more effective strategies for managing our global resources. Moreover, the existence of past civilizations reminds us that Earth's carrying capacity is not a fixed number, but a dynamic concept influenced by technology, resource management, and environmental conditions. This understanding encourages us to approach global sustainability with greater urgency and innovation, recognizing that our actions today will shape the planet's ability to support future generations. Considering the needs of a civilization lasting millions of years forces us to think on an unprecedented scale about resource management. Such a long-term perspective reveals the true finite nature of many resources we currently take for granted. Materials we consider abundant today, like certain metals or minerals, could become scarce or depleted over millennial timescales. This vast timescale also highlights the importance of sustainable practices and circular economies. A civilization enduring for millions of years would need to master the art of recycling and reusing materials with near-perfect efficiency. They would likely develop technologies to extract resources from increasingly difficult sources, such as mining asteroids or processing materials once considered waste. Energy production becomes a critical concern over such extended periods. Fossil fuels, which currently dominate our energy landscape, would be exhausted relatively quickly on this timescale. A million-year civilization would need to rely entirely on renewable or nearly inexhaustible energy sources, such as advanced solar, fusion, or even more exotic power generation methods we have yet to discover. Lastly, this perspective emphasizes the need for long-term planning and decision-making. Policies and practices would need to consider impacts not just decades or centuries ahead, but thousands or even millions of years into the future. This could lead to a radical shift in how we value and manage resources, prioritizing ultra-long-term sustainability over short-term gains. The Silurian hypothesis, which proposes the possibility of an advanced civilization existing on Earth millions of years ago, challenges our understanding of Earth's history and could significantly impact our approach to geoengineering and climate mitigation. If we seriously consider the implications of this hypothesis, it prompts us to re-evaluate the long-term consequences of our actions on the planet. The idea that a previous civilization might have altered the Earth's climate and environment to the point of their own extinction serves as a stark warning about the potential risks of large-scale geoengineering projects. This hypothesis encourages a more cautious and holistic approach to climate interventions. It suggests that we should thoroughly investigate the long-term effects of our proposed solutions, considering not just immediate results, but potential consequences that might unfold over thousands or even millions of years. The Silurian hypothesis reminds us that our understanding of Earth's systems is limited, and unintended consequences of our actions could be far-reaching and potentially catastrophic. Moreover, this concept underscores the importance of preserving and studying Earth's geological record. If evidence of a previous advanced civilization could be overlooked, it highlights the need for more comprehensive and interdisciplinary approaches to Earth science, combining geology, climatology, and even archaeology to gain a fuller picture of our planet's history and potential futures. The collapse of an advanced ancient civilization due to environmental factors offers valuable insights into the delicate balance between human societies and their ecosystems. Such a scenario highlights the critical importance of sustainable resource management and the potential consequences of ignoring environmental warning signs. One key lesson is the need for long-term planning and adaptability in the face of changing environmental conditions. An advanced civilization that fails to anticipate or respond to ecological shifts may find itself vulnerable to resource depletion, climate changes, or natural disasters. This underscores the importance of developing resilient systems and technologies that can withstand environmental pressures. Another crucial takeaway is the interconnectedness of human activities and natural systems. The hypothetical collapse serves as a stark reminder that even technologically advanced societies remain dependent on the health of their ecosystems. Overexploitation of resources, pollution, or large-scale environmental modifications can trigger cascading effects that ultimately undermine the very foundations of a civilization. Furthermore, this scenario emphasizes the value of preserving knowledge and learning from past experiences. By studying the factors that led to the downfall of an ancient advanced civilization, modern societies can gain invaluable insights into sustainable practices and potential pitfalls to avoid. This historical perspective can inform current decision-making processes and help shape more resilient and environmentally conscious societies for the future. The idea of ancient advanced civilizations challenges our understanding of human history and our impact on Earth. This concept suggests that long before our current era, there may have been societies with technological capabilities rivaling or even surpassing our own. Such a possibility forces us to reconsider the timeline of human progress and our relationship with our planet. If ancient advanced civilizations did exist, it would imply that humans have been capable of significantly altering their environment for much longer than we currently believe. This could mean that human impact on Earth has been more extensive and prolonged than previously thought. It raises questions about long-term environmental changes and whether some of the geological or climatic shifts we observe today might have roots in these ancient societies. Moreover, the existence of such civilizations would suggest that technological advancement and decline can occur in cycles. This perspective encourages us to view our current civilization as part of a potentially repeating pattern rather than a unique pinnacle of progress. It prompts us to consider the sustainability of our actions and the potential consequences of our technological choices over extended periods. Ultimately, the concept of ancient advanced civilizations invites us to adopt a more humble and cautious approach to our role on Earth. It reminds us that our current impact, while significant, may not be unprecedented, and that we should learn from both the achievements and potential downfall of those who may have come before us. The Silurian hypothesis serves as a thought-provoking concept in discussions about the Anthropocene era, challenging our understanding of Earth's history and human impact. This hypothesis explores the possibility that an advanced industrial civilization might have existed on Earth millions of years ago, long before humans evolved. When considering the Anthropocene, scientists typically focus on the profound changes humans have made to the planet in recent centuries. However, the Silurian hypothesis encourages us to consider a broader time frame and question our assumptions about past civilizations. It asks whether we would be able to detect evidence of an ancient, technologically advanced society if it had existed in the distant past. This idea relates to the Anthropocene by highlighting the potential long-term effects of industrial activity on the planet. If an advanced civilization had existed millions of years ago, what traces might it have left in the geological record? This question prompts us to consider how our own civilization might be detected by future scientists millions of years from now. The Silurian hypothesis also underscores the importance of understanding the lasting impacts of human activity on Earth's systems. It encourages us to think critically about the markers we are leaving behind and how they might be interpreted in the distant future, providing valuable perspective on our current discussions about the Anthropocene and its long-term implications for our planet. The Silurian hypothesis proposes an intriguing possibility that challenges our understanding of Earth's history and the search for extraterrestrial intelligence. This concept suggests that an advanced industrial civilization might have existed on Earth millions of years ago, long before humans evolved. The name is inspired by the fictional Silurians from Doctor Who, an advanced reptilian species that predated humans. This hypothesis relates to the search for extraterrestrial intelligence in several fascinating ways. Firstly, it encourages us to broaden our perspective on what alien civilizations might look like and where they might exist. If an advanced civilization could have thrived on Earth without leaving easily detectable traces, the same could be true for other planets we are investigating. The Silurian hypothesis also highlights the challenges in detecting long-lost civilizations, both on Earth and potentially on other worlds. It suggests that we may need to refine our search methods and expand our criteria for identifying signs of intelligent life. This could include looking for subtle geological or chemical signatures that persist over millions of years, rather than focusing solely on current radio signals or visible structures. Furthermore, this concept underscores the importance of considering deep time in our search for extraterrestrial intelligence. It reminds us that civilizations might rise and fall over vast timescales, and that the window for detecting them could be relatively brief in cosmic terms. This realization adds urgency to our search efforts and emphasizes the need for patience and persistence in our quest to find evidence of intelligent life beyond Earth. The potential existence of ancient Earth civilizations introduces a fascinating twist to our understanding of the Drake equation. This equation, formulated to estimate the number of communicative extraterrestrial civilizations in our galaxy, relies on several factors, including the fraction of planets that develop intelligent life. If Earth hosted advanced civilizations in its distant past, it would suggest that intelligent life might be more common than we initially thought. Consider the implications. If multiple civilizations arose and fell on our own planet over millions of years, it could indicate that the emergence of intelligence is a relatively frequent occurrence given the right conditions. This would potentially increase the value we assign to the factor in the Drake equation representing the likelihood of intelligence evolving. Moreover, the existence of ancient Earth civilizations would raise questions about the longevity of technological societies. If these civilizations existed but did not survive to our present day, It might imply that advanced societies face significant challenges in maintaining long-term stability. This could affect our estimates of how long civilizations typically last, another crucial factor in the Drake equation. Lastly, if evidence of these ancient civilizations has been largely erased by time, it suggests that detecting signs of past alien civilizations might be more difficult than previously assumed. This could influence how we interpret the apparent silence of the cosmos, potentially explaining why we have not yet detected signs of extraterrestrial intelligence despite the vast number of stars and planets in our galaxy. The idea of ancient advanced civilizations challenges our conventional understanding of cosmic evolution. While there is no concrete evidence for such civilizations beyond Earth, their potential existence raises intriguing questions about the development of intelligence and technology across the universe. If ancient advanced civilizations did exist, they could have potentially altered the course of cosmic evolution on a vast scale. These hypothetical beings might have harnessed the energy of entire stars or even galaxies, leaving observable traces in the cosmos. Astronomers and scientists actively search for signs of such large-scale engineering, known as techno-signatures. The concept also prompts us to reconsider the timescales of technological development. Our own civilization has made rapid advancements in just a few thousand years. An ancient civilization with millions or even billions of years of development could have achieved capabilities far beyond our current imagination, potentially including interstellar travel or the ability to manipulate the fabric of space-time itself. Moreover, the possibility of ancient advanced civilizations encourages us to broaden our search for life and intelligence beyond traditional methods. It pushes us to look not just for biological signatures but also for signs of technology and artificial structures on cosmic scales, expanding our understanding of how life and intelligence might manifest throughout the universe. The Silurian hypothesis challenges our understanding of Earth's history and the potential for advanced civilizations to exist long before humans. This thought experiment, proposed by scientists, considers whether an industrial civilization could have existed on Earth millions of years ago, leaving little to no trace for us to find today. This hypothesis raises intriguing questions about the longevity and detectability of civilizations across the universe. If an advanced society could rise and fall on our own planet without leaving clear evidence, it suggests that similar scenarios might occur on other worlds. The Earth has undergone numerous geological and climatic changes over its history, potentially erasing signs of past technological societies. Applying this concept to the broader universe, we might reconsider our expectations for detecting extraterrestrial civilizations. The window of opportunity for identifying technological markers from distant worlds could be much smaller than previously thought. Advanced societies might exist for relatively brief periods on cosmic timescales, making it challenging to detect them across vast distances. The Silurian hypothesis also prompts us to reflect on the resilience and sustainability of our own civilization. If past societies on Earth or other planets have risen and fallen without leaving lasting traces, it underscores the importance of developing sustainable practices and technologies that can withstand the test of time. This perspective encourages us to think more deeply about the long-term impact of our actions and the potential legacy we might leave for future inhabitants of Earth or other worlds. The potential existence of lost Earth civilizations introduces intriguing complexities to our strategies for interstellar communication. These hypothetical societies, which may have risen and fallen long before our recorded history, could have left behind messages or artifacts intended for future discovery, both on Earth and beyond. This possibility prompts us to broaden our search parameters when considering interstellar communication. We must now account for the chance that ancient terrestrial civilizations might have sent out signals or probes thousands or even millions of years ago. These signals could still be traveling through space, carrying messages from long-gone Earth inhabitants. Moreover, the concept of lost civilizations encourages us to reassess the longevity and resilience of intelligent societies. If advanced cultures existed on Earth in the distant past but did not survive, it raises questions about the challenges we might face in maintaining long-term interstellar communication. This realization emphasizes the importance of creating durable, long-lasting methods of message transmission that could withstand the test of time. The idea also highlights the need for a multifaceted approach to interstellar communication. While we continue to search for signals from extraterrestrial civilizations, we must also remain open to the possibility of discovering ancient messages originating from Earth itself. This dual focus could lead to new insights about both our planet's history and the nature of intelligent life in the universe. The Silurian hypothesis offers an intriguing perspective on the Fermi Paradox, challenging our assumptions about the detectability of past civilizations on Earth and potentially on other planets. This hypothesis suggests that an advanced industrial civilization could have existed on Earth millions of years ago, leaving little to no trace for us to find today. When considering the Fermi Paradox, which questions why we have not detected signs of extraterrestrial intelligence despite the vast number of potentially habitable planets, the Silurian hypothesis adds a new layer of complexity. It raises the possibility that we might be overlooking evidence of past civilizations, both on Earth and elsewhere in the universe, simply because we do not know what to look for over such vast timescales. This concept forces us to reconsider our methods for searching for extraterrestrial intelligence. If an advanced civilization could rise and fall on Earth without leaving obvious traces after millions of years, the same could be true for other planets. We might need to expand our search criteria and develop new techniques to detect subtle, long-term changes in planetary environments that could indicate past technological activity. Furthermore, the Silurian hypothesis highlights the potential impermanence of civilizations, suggesting that intelligent life might be more common in the universe than we think, but perhaps not persistent enough to maintain detectable signals over interstellar distances for long periods. This perspective offers a possible explanation for the apparent silence of the cosmos, aligning with some proposed solutions to the Fermi Paradox that focus on the transient nature of technological civilizations. The discovery of ancient advanced civilizations on Earth would profoundly reshape our perspective on life in the universe. Such a finding would suggest that intelligent life can arise and evolve to high levels of technological sophistication multiple times on a single planet. This would challenge our current understanding of human history and technological development. If we found evidence of civilizations predating our own by tens or hundreds of thousands of years, it would indicate that advanced societies can emerge, thrive, and potentially disappear without leaving obvious traces. This realization would force us to reconsider how we search for signs of extraterrestrial intelligence. We might need to look for more subtle indicators of past civilizations, both on Earth and other planets. Furthermore, the existence of multiple advanced civilizations on Earth would imply that the conditions for intelligent life to evolve are not as rare as we once thought. This could significantly increase our estimates of the likelihood of finding intelligent life elsewhere in the universe. It might suggest that life, once started, has a higher probability of reaching advanced stages than currently believed. However, it would also raise questions about the longevity and sustainability of civilizations. If advanced societies existed on Earth before us, what led to their downfall? Understanding the factors that contributed to their disappearance could provide valuable insights into the challenges we might face and the potential pitfalls that advanced civilizations must navigate to survive long-term. Studying the possibility of ancient Earth, civilizations offers intriguing insights into the development of intelligence in the cosmos. By examining our own planet's history, we can better understand the conditions that might foster intelligent life elsewhere in the universe. One key lesson is the importance of environmental stability. Earth has maintained relatively stable conditions for billions of years, allowing life to evolve and diversify. This suggests that planets with long periods of stability might be more likely to produce intelligent species. However, our planet has also experienced numerous catastrophic events, such as asteroid impacts and massive volcanic eruptions. The resilience of life in the face of these challenges demonstrates that intelligence can potentially emerge, even in dynamic and occasionally hostile environments. The study of hypothetical ancient civilizations also highlights the potential impermanence of technological societies. If advanced cultures existed on Earth millions of years ago but disappeared without leaving clear evidence, it raises questions about the long-term survival of intelligent species. This concept, often called the Silurian hypothesis, prompts us to consider how we might detect signs of long-lost alien civilizations on other worlds. Furthermore, exploring the possibility of ancient Earth civilizations encourages us to broaden our understanding of what constitutes intelligence and technology. We might need to look beyond our conventional expectations to recognize signs of advanced societies, both on Earth and elsewhere in the cosmos. This expanded perspective could prove crucial in our search for extraterrestrial intelligence across the vast expanse of the universe. The Silurian hypothesis challenges our assumptions about the uniqueness of human civilization on Earth. This thought-provoking concept suggests that an advanced industrial civilization could have existed on our planet millions of years ago, potentially during the Silurian period, leaving little to no trace for us to find today. This hypothesis forces us to reconsider the possibility of multiple genesis events on a single planet. It expands our understanding of the potential for intelligent life to arise, thrive, and potentially disappear without leaving obvious evidence of its existence. The idea that Earth could have hosted more than one technologically advanced species over its long history is both exciting and humbling. The implications of the Silurian hypothesis extend beyond Earth. If multiple genesis events could occur on our planet, it raises questions about the frequency of life emerging on other worlds. It suggests that life might be more resilient and more likely to arise under various conditions than we previously thought. This could mean that the universe is teeming with life, perhaps even with multiple civilizations rising and falling on individual planets over vast timescales. Moreover, this hypothesis encourages us to broaden our search for signs of past civilizations, both on Earth and other planets. It prompts us to consider what evidence of our own civilization might persist millions of years into the future, and how we might recognize signs of past technological societies that differ significantly from our own. This shift in perspective could lead to new approaches in the search for extraterrestrial intelligence and a deeper understanding of our place in the cosmic timeline. The concept of cyclical civilizations challenges our perception of cosmic timescales, expanding our view beyond the linear progression we often associate with the universe. This idea suggests that advanced civilizations may rise, fall, and rise again over immense periods, potentially spanning billions of years. Considering cyclical civilizations forces us to grapple with truly vast timescales. While we often think in terms of human lifetimes or even the age of our own civilization, cyclical civilizations operate on a cosmic clock. The time between cycles could be longer than the entire history of life on Earth, dwarfing our comprehension of historical time. This perspective also raises intriguing questions about the nature of technological progress and the potential limits of civilization. It suggests that there might be natural boundaries or recurring challenges that cause advanced societies to collapse and rebuild repeatedly. These cycles could be driven by factors such as resource depletion, environmental changes, or even cosmic events operating on galactic timescales. Furthermore, the idea of cyclical civilizations intersects with our search for extraterrestrial intelligence. It implies that the window for detecting other civilizations might be much smaller than we previously thought, as advanced societies may only be detectable during specific phases of their cycles. This concept adds another layer of complexity to our understanding of cosmic time and the potential for intelligent life in the universe.